which have different fields combined together. And that is why if you look at the programs, you have different kind of fields, food sciences, bio, a lot of things combined together. Because when I was in KK in Japan, when I tried to move around, I discovered that there's most of the equipment that I can find in Japan. And even in Siam, in Thai, there's some part of equipment which I was trying to look at. How did they manage to achieve that? Then I discovered that then Africa need to combine together to work with belief, so that some also, we can also try to do a little things like that, and then we can be able to achieve our aims and our dream. And that is why this conference is very, very important for us, especially our continent, so that we can be able to have more knowledge and have different way of analyzing our sample until we be able to achieve our aims. Ladies and gentlemen, I would like to welcome you all to this conference, whether you are presenters or you are part of the audience, for this on behalf of all the organizing committee us to achieve is our aims. And I believe that we're going to enjoy all the talk throughout the program. So from then, I would like to hereby declare the African license for the 2023 open. Thank you. Over to you, Simon.
Thank you very much, Philip. So before I say something quickly about the African light source, there's something I quickly want to do, because we are not meeting in person. So I want to quickly share what we would be doing if we were meeting in person. I hope you can see my screen. Can you please confirm if you do see my screen?
Yes.
Yes.
Yeah, thank you so much. I wanted to introduce you to this calling stick. It's an African ceremonial calling stick. It comes from the ancient Ashanti culture, and it is the AfLS calling stick. And if we were in person, we would have it at the front of the auditorium, like we do have here. It's in the ancient culture. It is placed at a crossroads long before the conference, and everyone walking past would be called to the conference. And you also see gender diversity and gender equality, because the female figure is at the top and has also a banner, and the male figure also has a banner to show all are called and all can speak. Another thing is, in this ancient culture, there's a speaking stick, and we would share the speaking stick to the speaker. The chairperson would give the speaking stick to the next speaker, one to another, and that would give them the right to speak. And these are two elements of African culture that are particular to the African light source. And when we establish the African light source, these two elements will be front and foremost in the reception area. And is actually resident virtually with Philip, who just opened the conference, the calling stick and speaking stick. So I wanted to introduce that to you, and I hope we will be meeting each other in person soon, and everyone will be able to see that. Well, that's my short introduction of our ceremonial calling stick and speaking stick. And now I want to tell you a little bit about the light source. Our slides are up. You can download. You will find clickable links. These are our recent publications. They will detail our history. And we have a roadmap, which we've been implementing since 2015. The part in blue is community driven. It's got all the elements of broadening the user group and training, capacity building, conferences like this one, workshops promoting African scientists to go to synchrotrons, and then all of our new friends that we see here today, and building our network, and so that we can all help each other. And then we have the part where it's more interacting with African governments and Pan-African organizations. On the right, you can see a panel. We've got MOUs and letters of support with many, many, many partner organizations. Just to say, the AfLS, that's us, are not the only ones pushing for a synchrotron. And in this conference, there will be the voices of many other African professional societies or Pan-African bodies who also push for the African synchrotron. So it's a group of many, many people. And one aspect to highlight is to ask who is an African. And the very first Pan-Africanist, Kwame Nkrumah, he said that to be an African, you don't have to be born in Africa, but Africa should be born in you. So who's ever a friend of Africa, inside the continent, outside the continent, if Africa is born in them, then they are also African, and we can all work together. The three items that are highlighted in orange, I want to talk about in a little while. But just to show you, we have these conferences, and this is our 6th one, and it would be wonderful if we do in person again. But you can see here, Sekazi, I've seen him in amongst the audience here. He is holding the calling stick there. So it's important to say that Africa's made a really tremendous progress since operating at modern light sources in very, very high level. And this is just a smattering of incredible research, of which we'll hear so much more about. And we really want to emphasize that people always say you must have reached 300 users before you can start talking about it. And we think Africa has gone way beyond this. So I want to highlight that there are feeder facilities around Africa, and thank particularly the International Union of Crystallography, who have established so many crystallography laboratories around the continent. But there are these feeder facilities, and these are also on our website and clickable. And these are places which have the capacity to do bioscience. So you will have seen there's now a malaria drug and so on, vaccine, and a lot of this is participated in by Africans, and a tremendous amount of science coming from Africa with synchrotrons, developing drug targets, medical interventions of all kinds. And this is material science, and in particular geology, so and minerals research. So that's a very important part of Africa. So you can really see there's a lot of science that needs to be done by Africans, because if we don't do it, it's not going to get the full attention, be it Africa's disease burden or Africa's mineralogy. And we think that more than half the continent is already painted out, indicating that there's papers and theses coming from Africans. And this is a large number of medical linacs that are around Africa. So is over 300, to show some capacity for accelerators in instruments and control systems. You also see a collection of those here. So we are not starting from zero. And a very important thing is the existing regional facilities. So this is something very close to what we want to promote. And that's facilities that go beyond their own borders, already behaving like regional facilities. And you do see several of them here, and we'll hear from them. during the conference. And now to catch us up, we've had 3 strategic task forces that must report in a month. And these strategic task forces have been thinking about those 3 programs that you see there. There's the African beamline, that we want to be at a particular international light source. That African beamline is going to allow us to have tech transfer and build technological and engineering capacity, so it goes beyond the science that we're doing now. And the strategic task force isn't going to come to a conclusion, but just present pros and cons, wisdom, their experience of deep dive into that concept. So that's actually the same also for the other 2. There's the collective African membership of an international light source. So here we want to go towards governance. We would have African governments having a role on the council of the international light source, so that they would start learning exactly, how do you govern an international facility. Of course, not completely new to Africa because of the square kilometer array, amongst others, but very important to start building that experience. And African regional infrastructure, so the motto is leave no country behind of the Africa Union. And all countries must acquire competitive, globally relevant research infrastructure, obviously not to the level of a synchrotron, but something that enables competitive research, can be published in its own right, but also will be important training and feeder infrastructure to an advanced light source. So those 3 have their own special session at this conference. And then we've got our conceptual design report coming out. It's complete and we're just waiting for an opportunity to launch it. We want to launch it at a very significant event. There's a team led by Prosper Ngabonziza who is designing the launch. And when it is launched, hopefully a multi-science event, a Pan-African event of considerable prestige that we can be an event at. And that conceptual design report's got what you expect, the science case, the socioeconomic case, and technology case, and so on. But it does have a conclusion that we want a 4th generation machine and want to be very, very competitive. But maybe by then it's already 5th generation, who knows? So that summarizes that. And we'll also hear from compact light sources that what role these can play. These would be also something on the roadmap, a milestone, and absolutely not take away that the ultimate destination is the African light source. But it's very, very important to us to retain African excellence and have infrastructure that's able to attract the incredible talent that Africa produces, not to see it dissipate into the science diaspora. And what accelerator capacity do we have? You see a listing here. These are the accelerators in Africa. The biggest one is the Itembe Labs, and that's in South Africa. So I think then that's my very quick wrap. I wanted to highlight a stab at milestones. So we've never shown this at the conference before. Many thanks to Ed Mitchell for inspiring us to do this and for, in fact, drafting it. But you're for Light Source Conference and you can look ahead, and in 12 years, folks, we want to see an operational light source for Africa. And 2026 is very, very big. 2026, a lot of the activities we're doing now will have culminated. So the strategic task forces. We'd like to see actually a realization of the work that we're laying down now. And then we'd like to improve our audit capacity of African science so that we really can showcase it. We'd like to have an executive office. We want to professionalize the African light source. We want it to be institutionalized and professionalized. So I'm leaving you with this slide. It shows you where we want to be, and it can focus our attention for this conference. In this conference, we will have opportunity to hear both about science and equipment and the policy towards the African light source. So from my side, I wish all of you and us a wonderful, wonderful conference, and thank you all for your participation. I stop my share now.
All right. All right, Simon. Thank you very much for this speech. Yeah, I think the next person we will be expecting is Prof. Amadeo, from the African Physical Society. Thank you.
Thank you very much, Professor Philip Olajo. Hello, everyone. It is a great pleasure and privilege for me to take the floor at the African Light Source and African Physical Society third joint meeting. The first one was in 2021, the second in 2022, the third is now in 2023. And before that, African Physical Society have organized an international conference and also online conference on 2020. And on 2018, we have organized in-person meeting in Rwanda in collaboration with ICTP, with the launching of the East African Institute for Fundamental and Applied Research in Physics, which is an ICTP institute. So we, as I say, it is a great privilege for me to talk now at this third meeting. And first, I would like to thank all the organizers, the AfLS President, Professor Simon Connell, and Executive Committee of African Light Source for permanent commitment for the realization of African synchrotron light source in Africa. And especially, I would like to thank also our friend from the US, Lawrence Norris, Sekazi Mitingwa, for their tremendous effort for the development of science organization and also for science project in Africa. And in addition, I would like to thank my colleague from African Physical Society for their commitment to make African Physical Society a Pan-African society, from north to south, from east to west, from all African diaspora at the service of Africa. And also, I want to thank all the people, especially the South African Institute of Physics, together again with Norris and all the others acting bodies for making all the connection and Zoom meeting of this conference to be possible. So on behalf of the African Physical Society, I would like to say that it is great to see again African Physical Society and African Light Source together for the organization of international conference in Africa in physics and physical science. We have to maintain this kind of activity in working together for the progress of science in Africa, for the benefit of our population. Today, the African physical community, I can say the African science community in general, have to play a first role to bring energy and light to African population, to bring health and economic progress for the well-being of everybody in Africa. It is a big challenge but only together we can overcome all of them. AfLS and AfPS are showing the way to go. Even I can say that last week I was in White River in South Africa, participating at the optic and photonics in Africa. And it was an occasion for me to underline the role of we have to play African scientists for the development of all the field of science in Africa. And I think that in this adventure of optics and photonics in Africa, the LAM network, the African Laser Atomic Molecular and Optical Science Network, the African Physical Society, the African Light Source have to play a major role for the realization of this photonic and optic initiative in Africa. So to finish my talk, I would like to send my best wishes for a very soon realization of African synchrotron facility, and best wishes to African Physical Society in bringing together all the physical society of the continent for the development of physical science in Africa. Thank you very much for your attention. Okay, I have finished.
Thank you very much, Prof. Amadou. We really appreciate your speech. And I think if we look at the and now trying to be having some of our so I'll be the one to share this session. So from then, want everyone, if there's any questions or anything that you want to ask the speaker, feel free to drop it on the via chat, that at least we can be able to attend to it, depending on time. Then our first speaker, talking about Dr. Jian from Sesame, and she'll be talking about Sesame BMO2 IR microscopy beamline, planetoria of opportunities. So over to you, Jian.
Thank you so much, Philip. Can you please confirm that you can see my slides?
Yes.
I can see your slide.
Yes, yep.
Yeah. So thank you so much. I also extend my thanks to the organizers and all the colleagues of organizing this annual conference of the African Light Source. And just to introduce myself, I'm working at Sesame Synchrotron Light Source. I'm the infrared beamline principal scientist, but I'm also helping somehow in the process of the establishment of the first African light source. The presentation is around the different opportunities that the infrared beamline at Sesame can deliver. So please let me first introduce Sesame as a facility. So Sesame is the acronym of the Synchrotron Light for Experimental Science and Applications in the Middle East. It's intergovernmental organization located in Jordan, and it's operating as a third generation light source, offering different techniques and different scientific advancements. Speaking about advancements, these kind of infrastructures are really considered now as being revolutionizing the fundamental and applied sciences. And this extends to a huge set of domains, like what you see here is biology, biomedicine, all the basic sciences, chemistry, physics, and climate change, environmental, pollution, water pollution, air pollution, also cultural heritage, archaeology, and also we can deliver a lot of important information on energy systems, catalysis, and engineering, including nanotechnology and other discoveries in industries. not only advancing scientific domains, but also these kind of infrastructures as synchrotron light sources can be a fundamental pillar of advancing capacity development, research, education, and they can also shed some light on the social and economic impact on any society. Of course, we are speaking in this conference about the African context, but also this can be extended to beyond. Among the different impacts that such a facility can deliver to Africa is something can be expressed as direct or indirect impacts. And some examples for this is like enhancing the employment record, minimizing the gender gap, opening more links between society and industry, and this of course will enhance the income at the different countries. So far there are almost around 60 of these facilities. Those are all having their common purpose and common values. They are working as democratic environments for scientists everywhere. And the only parameter that these infrastructures rely on is the scientific merit. As you see here, Africa is the only continent that is left behind without this advanced technology. And what we are working on tirelessly now is to establish the first African light source in the continent. The development of such infrastructures has also passed through different stages of development based on the technology, of course. And now the people are speaking about third generation, fourth generation light sources. So this is something is also taken into account when people are working on establishing the African light source. As I said, these kind of facilities are called synchrotron light sources. So they are relying on as called synchrotron radiation, which is electromagnetic radiation as emitted by charged particles moving in a curved trajectory at a speed close to the speed of light. And this opens a lot of opportunities, technologies, and also complementarities between these. The radiation that's produced at these facilities ranging between X-rays, ultraviolet, visible, and also infrared, which is the scope of this presentation. Synchronous radiation itself was noticed as Crab Nebula 6,000 light years ago, but also light years away, but also it was observed in 1947 in the labs in the advanced light source for the first time. A general or schematic structure of such a facility starts with mainly an injector of particles that are electrons and principal, as our case here. Then a booster, that means boosting the energy to a higher energy as per the design. And then the third element is what is called storage ring, which is the ring that delivers the highest energy of the accelerator that is based on. In our case, it's 2.5 gigaelectron volt. And of course, each facility is designed different based on different technology or different resources and targets. Let's say that the end product of the facility is what's called beamline, and the beamline is comprising experimental end stations delivering different techniques. So around the or surrounding the storage ring, there are beamlines. Again, number of beamlines is based on the resources of each facility and design. And they can range between X-rays, hard X-rays, soft X-rays, infrared, ultraviolet, whatever technique is implemented. And each technique is delivering special energy and special requirements for the experiments as demanded by the users of the facility. The synchrotron radiation is also comprising, as it's comprising broad electromagnetic spectrum. It also has very unique properties. Among them, what you can see here is the high collimation. That means we can attain high flux of the photons. And also the brilliance or brightness is also very important for many applications, as for example here the spectroscopy again. It has a wide tunability. It has polarization, fast time structure that also allow for different applications that are quite impossible to be done with conventional facilities. As I said, as we are dealing with X-rays or infrared photons, there are different mechanisms of interactions of these photons with matter. So it's based on the interaction of the photon with the samples. That means we can have either reflection, diffraction, photon emission, fluorescence, absorption, dispersion, or small angle dispersion as well. And this again gives a lot of information about samples, structures, properties, and functions. And we can tailor all these interactions or categorize them under some main categories such as spectroscopy, scattering, or also imaging. Back to Sesame and the infrared beam line here. Sesame is designed to accommodate per design 18 beam lines so far. We have 5 operational beam lines. So we started the operation of the facility with the EXAFS X-ray fluorescence beam line in 2018. Followed also by the infrared microspectroscopy beam line, then the material science for powder diffraction, X-ray powder diffraction technique. And then the recent 2 beam lines, those are installed and are at the commissioning phase, will be open to users next year, are the BEATS, which is the beam line for tomography at Sesame, which is a project of consortium of 9 partners, including the EU. And also the HAZIP, which is a Helmholtz Sesame beam line for soft X-ray spectroscopy. And again, it's a collaboration between Germany, Helmholtz institutions, and Sesame. So for the infrared, I simply, when I try to pick the attention to the difference between the conventional infrared spectroscopy and the synchrotron infrared spectroscopy, I found that this image is quite expressive, and it's how it's representing the difference in resolution between the Hubble and the James Webb telescopes. And of course, this means we can see better, we can see more information, and we can also monitor the smallest or the tiniest details and differences between different samples. So it's all about resolution parameter. For this beam line, which is the BM02, which is located at the cell 2 and the storage ring of Sesame. The beam line was designed in 2016 in collaboration with the French synchrotron Soleil. The beam line was also, beam line components were also fabricated in France in 2017, followed by shipping to Sesame for installation and commissioning. And then the beam line came into service for the users from the region and also beyond in November 2018. At that time, Sesame was the first, so the IR beam line was the first fully designed beam line. And its mission actually is ranging between accepting the regular proposals submitted in our calls for proposals. Those are announced twice a year now. And also performing in-house research and collaborations with other researchers from the region. Also, if there are kind of resources, I mean, financial resources, and also time constraints, we can allow training fellowships as well as accepting national and international collaborations. Infrared spectroscopy is a well-known technique in chemistry, and it's basically a vibrational spectroscopy technique that relies on the interaction of the photons with the material, and the level of interaction is around the molecules. So of course, each radiation has its own limitations in its interaction with matter. So it's like X-rays when dealing with atoms, or X-ray difflection with atoms, X-ray fluorescence with elements, and for us, we are working with molecules. So as I always say, there is nothing called a technique is better than another. It's a matter of the question of the experiment and what are the answers that you are looking for. And again, the basic phenomenon that occurs here is the absorption. For a technique to serve as an ideal technique for a specific experiment, it should have kind of features. Those are summarized here. Basically, it's favorable to be a non-destructive or non-invasive technique, and this is, of course, very important for many kinds of samples, such as biological or archaeological samples. And it can also be fast and cheap for the users. I can explain at the end of this talk what do we mean by cheap here, because these facilities cost millions, but cheap is a relative issue here. It can also be universal technique. That means different objects can be studied with no sample pre-treatment or preparation, or at least minimal preparation and manipulation. It has to be versatile. That means also local information of small areas and composition needs to be assessed. And this means we need spatial resolution for that. And synchrotron is the best tool here. It should be also sensitive to be able to detect trace quantities, and it should be also multi-elemental. That means simultaneously detect multiple components in a single measurement or a single shot. And here I already spoke about the IR spectroscopy as being a universal chemical technique. And here you can see that it can be used for structural analysis, giving information on bond conformation, bond environment, bond orientation, and also to the order, giving some information on phase or crystallinity. Qualitative analysis, quantitative, and also for more specific applications such as electron energy, or for the non-destructive demands for studying the effect of temperature or pressure, irradiation, or material aging, reaction kinetics. This technique is also important, and it helps a lot in finding so many chemical information. Again, apart from the conventional infrared spectroscopy that is well known for everybody as spectra, usually people collect what's called triplets. So they collect like 3 spectra per sample to ensure that these measurements are reproducible. For us here, we are working with microscope. So that technique is called microspectroscopy. It's combined technique, and it combines both microscopy plus spectroscopy. And with this, we are able to collect hundreds or thousands of spectra. And this helps a lot in many applications, such as biological applications or biomedical applications, where we really need a huge set of statistical information to be able to give a definitive analysis or answer to the question of the study. Another advantage that we can do with this technique is to do infrared chemical mapping and chemical imaging. And this is again cannot be attained without a microscope, without infrared microscope. And also for this kind of chemical mapping, it gives a lot of information about, I always say it like the geography of the sample. So it gives you the concentration of all the functional groups in the sample. It gives information about the distribution. It gives information about the margins between the function groups. It gives information about the ratios of all the functional groups. So these chemical maps are based on the absorption. So the colors are meaningful for us. It's based on the intensity of the absorption of the IR interaction with the sample. Of course, there are different applications that can use this, I would say, modality or method. And what you see here is an example for a chemical mapping of ancient tooth sample. But you see on the right, let me try to get my laser pointer, and I hope you can see it. This is a visible image of the cross-section of ancient tooth. And the one to the left is its chemical IR. Of course, you see that they are identical in shape because IR is working on the same cross-section, but it's showing us the invisible chemistry of the sample. And here it's also important to monitor the different layers of the tooth. So spectra here are not enough. Here you need an infrared microscope because you need to study or investigate the different layers. For example, here for the cross-section of the tooth, the external layer is the enamel, and the internal layer, there is the dentine, and then going also deeper, we have the cementum. So you need to see it. So this is why you need to have the microscope to monitor each layer and to get information separately on each layer of the cross-section. This is another example, which is measuring the chemical map of cross-section of a modern hair. So this is cross-section of a single strand of hair. And also to do this, you need to have a very specific beam size to do that, because you need to go down with the beam to the dimensions of this hair cross-section. And here again, the synchrotron is the tool for that, because conventional infrared is impossible to be useful here. And again, to have this slide also for you, you can check the uploaded presentation after this. The major advantage for the synchrotron is the high brightness, which is around 1,000 times brighter than the conventional infrared source. And this, of course, allows for a lot of important development in the mid-IR and the far infrared regions, which are extracted here at SESAM. And again, the three major factors that we are benefiting a lot of infrared spectroscopy at synchrotron facility that are the spatial resolution gained, better signal-to-noise ratio, and faster data collection. And again, this allows a lot of modalities such as spectroscopy, microscopy, polarized microspectroscopy, and time result studies. These are the a few technical information that you can read in the presentation afterwards. This is how we are extracting the synchrotron infrared from the storage ring. And these are some also information to pick your attention to the difference, the real and the deep difference between the synchrotron infrared and the conventional infrared. You can look here at the upper, the top figure for the signal obtained for the synchrotron, which is the red one, compared to the blue one that's obtained by the glober, that's conventional infrared. You see how far we are gaining the signal. And again, the bottom left is showing again the superiority of the synchrotron radiation infrared with respect to the conventional sources when we want to go down with the beam size to be able to study the very tiny details of any sample. And the bottom right is showing you what we mean by enhancing the signal-to-noise ratio. That's the red is the noise level, noise RMS of the synchrotron, and the blue is the noise RMS of the global, which is the conventional. Again, you see that the signal or the, let's say it this way, the noise that you get with the conventional source may be a real signal, but you don't see it. This is why you need the synchrotron. These are also a few examples to show you again the superiority between the synchrotron and the conventional for two different domains like biology and also the material science or mineralogy samples. This is the infestation of the beamline. It comprises Hyperion microscope and vertex FTIR spectrometer. And we are able also to work with different kinds of samples, different kinds of, I would say, preparation. So we can work in transmission or reflection to accommodate each samples. A major advancement that we are heading to soon, we are waiting for the shipment of this detector. This is called focal planar ray detector. And it advances, as it always says, in the future of the chemical infrared imaging, that in one shot, all at once, imagine that you are having 64 by 64 detectors instead of just a single detector. Different domains are received at the beamline to be studied by our users from life science, archaeology, material science, astronomy, astrophysics, veterinary science, also anthropology, forensic, and engineering and technology. This is a workflow for the FTIR microspectroscopy. I put it also for your reference afterwards. You need to get some information on the sample preparation, sampling mode, data acquisition, and data analysis as well. Again, no matter what the sample shape or thickness or size is, we are able to work with different modalities, and those are transmission and reflection. There are different sample manipulation accessories to work for bulk or solid or liquid or thin film or whatever the sample is also are available. And again, a set of different software for data processing and analysis. Our users are actually coming from different regions, not only the Middle East, but also from abroad, such as Malta, Germany, Italy, France, Belgium, Colombia, Malaysia, Japan, UK, and also some new Arab countries are starting to demand some experiments. I'm taking you now in the last remaining minutes for the title of the presentation, which is Plethora of Opportunities. And first, you can get back to the presentation, and some publications are also available on the internet. So among our studies is this one, which is quite interesting one on the preeclampsia disease. For women, we here try to investigate the structure of the placenta and to understand the role of the placenta in evolving this disease. We also worked on type 2 diabetes and diabetic nephropathy using plasma of the blood of type 2 diabetes patients. And again, we went back to the preeclampsia, and here we worked not on the placenta tissues itself, but we worked on also the plasma of healthy, non-pregnant, pregnant, and diseased pregnancy also cases. We also have some information on the induced Alzheimer's disease in rat brain cortical tissues. And here we investigated the effect of some plant seeds on the evolvement of the proteins responsible for the Alzheimer's disease. Here we also monitored some hormonal changes in mice skin related to the stress hormone, leptin. And here we worked on unfolding behavior of collagen nanofibers. This is very important for the regenerative medicine applications. Here we tried also to get some insights on Alport syndrome, which is a kidney disease that's with incidence 1 to 5,000 births. This disease is not understood so far, the mechanism of its pathology, and also the treatment is not yet assessed. For cultural heritage, we worked on, again, human hair from the Roman period. And again, the aim was to assess the preservation status and alterations of organic compounds of these cross sections. And we worked also on mummified skin of a head that had skin that was diagnosed with skin disease, but was not confirmed. But with infrared synchrotron radiation, we confirmed the skin disorder. Here we worked on organic compounds in the Nabatean wall paintings from the archaeological site of Petra in Jordan. And here we worked with users from Iran on ancient wool. And the aim here was to identify the different pigments and colors and dyes used to color these ancient wool for these ancient mummies. Again, for Egypt, we worked on different samples for different coffins, like pigments, binders, and mummification materials. And here from Jerusalem, we worked on characterization of a 16th century Ottoman tile from the Dome of the Rock. And here again, another wall painting. This is a nice collaboration between Egyptian and Belgian users to work on this polymeric consolidant of this wall painting. Again, art restoration, infrared synchrotron can also be a useful tool to give information on how to restore back the archaeological icons. This is on Islamic historical parchment manuscripts from Iran. And here the target was cellulose of the paper and also the ink that was used to write these manuscripts. A huge project on diagenesis and ancient human bones from Cyprus, from the Mediterranean and the Near East region. And again, archaeological bones for non-adult and adult humans from Cyprus. And again, skin, ancient human skins for this king cabinet. We are also had some information on that. And again, some 19th century historical photographic glass plate from Iran. And heading next month with some users working on Antarctic meteorites to understand more about the composition of these meteorites. Last highlight is to show you also that we are heading to understand more about the ancient fossil record of Earth and potentially Mars, with a group of users from the National History Museum in UK, from UK, Kurdistan, and Iraq. And we're going to study stromatolites, showing 3.5 billion years old from Western Australia. Of course, this beamline has been benefited from a lot of international experience, collaboration, and cooperation. And among the people that we are thankful for are Soleil Synchrotron in France, INFN, Istituto Nazionale di Fisica Nucleare in Italy, IAA, and of course, all the staff of Sesame. And I would like to take a minute just to invite every one of you to please be a part of our team in the ASFAP Light Sources Working Group, which is the African Strategy for Fundamental and Applied Physics. We would like to receive more information about your requirements, about your opinions, about your demands for an African light source. There is the link of the survey. And again, I would like to, before thanking you, of course, for your attention, I'd like to invite you to another recent survey that we launched. This is the link at the bottom of the slide for Africa. This is for the African Infrastructure Task Force. And we would also like to hear more from you about your demands and perspectives. Thank you so much for your attention, and I leave my email and also the presentation for any question. Thank you so much.
Thank you, Jan. Thank you for the excellent presentation. And then I think I will take a few minutes. I just want to talk about the sample sizes. Any idea about the sizes, the size for the sample?
The size for the samples?
Yeah, if somebody wants to make use of the such a beamline.
Yeah, if I understand well, you're asking about the size of the sample to be measured at the beamline, right? Yeah.
Yeah.
Yeah. So the size of, I mean, for us, for the infrared, it's not a problem at all because we can, because basically we are working with microscopy. So the very tiny piece of sample for us under the microscope is really a huge one. And we can section the sample if it's possible to section it. We can work on its powder. If it's bulky and we cannot break, we cannot section, we cannot powder, we are also having an accessory. It's called attenuated total reflection accessory. And with this, we just come on the sample as it is without any manipulation, without any preparation, and just get in contact with the crystal with the sample and measure. So the size is not a problem. The thickness is not a problem. Yeah, and also the form is not a problem.
All right. Thank you very much. I believe if there's any questions to be dropped on the chat for you, that I can be able to contact the person.
Thank you.
Directly. I really appreciate for turning up every time we call on you. Thank you, Jessica.
Thanks.
All right. I think I would like to, yeah, so I would like to thank you, Jan. So then I would like to call our next plenary speaker in person of Professor Gilbert, and Gilbert from the University of Wisconsin, United States of America. So he'll be talking about coral reef formation from nanometers to kilometers. Now the floor is yours, Prof. Gilbert.
Thank you very much, Philip, and thank you very much, Simon, for inviting me. I'm really excited to be giving this talk. I'm really excited about the African light source, and I'm very happy to have been given the speaking stick for this conference. So I'm going to share with you a few ideas on how corals form their skeletons, all 1 nanometer at a time, but then up to an enormous scale, as you can see in this image that I've captured back in 2006 in Australia, where Maybe you want to restart that? The recording stopped. Great. So from nanometer to kilometers, we're in Australia. The Great Barrier Reef is 2,400 kilometers from north to south. So that is by far the biggest biomineral on Earth. It's visible from outer space, and it's all formed one nanoparticle at a time, one ion at a time, by very many corals in parallel. So to understand corals, let me give you a tiny little introduction about them. They are part of the phylum Cnidaria, along with anemones and jellyfish, and they have these tiny little polyps that are about a millimeter in size, and they can have either a multiple of 6 tentacles or a multiple of 8 tentacles, in which case they're called hexa or octocorals, and they all form hard skeletons. Sclerotinian corals, especially all of the hexacorals, form hard skeletons that are invariably made of aragonite. They're incredibly complex. They have these polyps that's about a millimeter in size with their tentacles, just like an anemone, but as a difference compared to an anemone, they actually deposit these hard skeletons, and these are very highly structured, and the morphology of those skeletons is very, very different across the different species of corals. So if you look at the surface of a coral skeleton, here the polyps have been removed, you can see these beautifully radial structures. Each one of these is a corallite. It's formed by one polyp, genetically identical to this other polyp that formed this other corallite, and genetically identical to this one and that one, and so on. Different species, different morphology, as you can see, but there's always the radial symmetry to it, and this star-like morphology and beautiful appearance, again, at the millimeter scale. But we're going to zoom in, and we're also going to zoom out to compare to this scale, and so bear with me as I go across scales. I mentioned that invariably the hexacorals that form hard skeletons form aragonite skeletons, and those are made 99% by weight by aragonite and 1% by weight by proteins. Aragonite looks like this. This is the unit cell of aragonite. You see calcium, carbon, and oxygen atoms, and you see this beautiful structure. Whereas geologic aragonite looks like this at the centimeter scale, where the z-axis that I'm going to be referring to afterwards is always along the long axis. So if crystals grow like needles, in this case like prisms, the long axis is the z-axis. So coral skeletons provide the structure necessary to build entire coral reefs. So there's a reason that coral reefs are called the coral reefs, and it's because they need corals to form. They're an incredibly diverse community, and there are a lot of different organisms, but the key ones without which no coral reef can form are corals and coral skeletons in particular. This is why it's so interesting to study the coral skeletons. The coral reefs only cover 1% of all ocean floors worldwide, and yet they host 25% of all known marine species. This tells you there is a tremendous amount of diversity that's hosted by coral reef ecosystems. They provide coastline protection, fishing, the fishing industry, and the tourism industry. And collectively in the US, where I'm speaking from, this provides $3 billion per year to the US economy and $3 trillion per year to the world economy. This is the gross national product of 1 year in France. So losing coral reefs, which we will do if climate change continues to go as it is obviously a tremendous loss, economic and otherwise, a tremendous loss of biological diversity and physical protection for coastlines and tremendous cost to humans. Coral reefs are threatened by ocean acidification and ocean warming. Both of these are due to too much CO2 in the atmosphere, so they are both due to climate change, and there is no question that that is anthropogenic. It's humans that put too much CO2 into the atmosphere too quickly, not only in terms of amount. Paleontologically, there has been more CO2 in the atmosphere, but the amount always varies more gradually than it is varying right now. So let's zoom into the nanoscale. It is amorphous calcium carbonates, or ACC, precursors that form coral skeletons. So when the animal, that polyp with the tentacles, deposits the skeleton, it doesn't deposit one ion at a time. It deposits one nanoparticle at a time. And this is one nanoparticle, that's another one, that's another one. This is the beginning of the coral skeleton. So you see that on the surface of the coral skeleton, there are these amorphous precursors that I labeled amorphous calcium carbonate hydrated, amorphous calcium carbonate dehydrated, and finally, the aragonite bulk skeleton. So you see that in blue is the aragonite bulk skeleton that's down here. On the surface, there are quite a few of these red and green pixels associated with the amorphous precursors. And of course, the nanoparticles formed by the animals and deposited on this forming surface are all much more amorphous than anything we ever find in the skeleton. Please note that these are 24 nanometer pixels, so that's approximately a 1 micron nanoparticle. These amorphous precursors, as you saw in that tiny little image, are invariably on the surface of coral skeletons. So here we're looking at 3 completely different genera of corals, Acropora, Stylopora, and Turbineria. And if you look at the bulk, it's mostly blue pixels, meaning aragonite minerals, whereas on the surface, we see these amorphous precursors. And if we zoom in on these boxes that are 5 by 5 micron, we see with 60 nanometer pixels that there are lots and lots and lots of amorphous precursors. I should notice that I removed the blue from this slide, so you can actually focus only on the precursor phases. If the material has already matured to the fully crystalline aragonite, it's completely blue, and I've removed all of the pure blue from these slides. So you can see that there is a layer with different thicknesses depending on the different corals, but so on average with Acropora it's 2 micron, and then about a micron with Stylopora and Turbineria, but invariably it's at the surface. In the bulk, you don't find any of these amorphous precursors. We map them because, thanks to a synchrotron, we can scan the photon energy, therefore going through absorption thresholds, in this particular case, the calcium L edge at approximately 350 electron volts. We see that the line shape of the spectra is completely different, whether we have amorphous calcium carbonate, hydrated, anhydrous, or crystalline calcite. And you see that color-coded exactly with the same colors that I'm using in the images. These 3 spectra are distinct, especially in this region labeled 2 and 4. That's why we need a synchrotron. But the key to saving coral reefs from climate change is to actually understand how corals form their skeletons. And this we've done with my brilliant graduate student who just defended a couple of weeks ago, and he's now Dr. Chen-Hyu Sun, and he imaged these beautiful coral skeletons and the forming surfaces. As usual, you see the very few pixels are on the inside of the bulk. Most of the bulk of the skeleton is blue, but at the surface, you have these 20 nanometer pixels this time, higher resolution. They're all on the surface and they're all amorphous. There is another method called the polarization dependent imaging contrast mapping, or simply PIC mapping, that I introduced a few years ago, that helps us tremendously understand the structure of corals. By structure, I mean how the crystals are oriented at the nanoscale. Once all of this material is crystallized, it's homogeneously blue when you map it with component mapping, so the chemical mapping, whereas the orientational mapping shows completely different structures. You see in particular that these are called centers of calcification, and they move along this tortuous line from here to here to here to here. You see that they are much more nanoparticulate along these centers of calcification, and then they start radiating from those centers of calcification radially as with acicular crystals, so with needle-shaped crystals away from these centers, and they are called spherulites. Even when these spherulites come and these acicular crystals come towards us, we can still tell that they're spherulitic in nature because the colors vary gradually. Just like in this radially distributed ones, we see that it goes gradually from green to cyan. Here we go gradually from blue to magenta to red, blue, magenta, red, blue, magenta, red in the next trabecula, even when they're oriented towards us. So we know that 100% of the structure of the coral skeleton is actually built of spherulites. So the corals all form skeletons at the nanoscale, but many, many corals in parallel form entire reefs. And those reefs offer shelter to entire ecosystems. And so starting from the nanoscale, going to the microscale of the PIC map I just showed you, and then the three-dimensional structure at the centimeter scale, which is what's most relevant from the fish point of view. You can imagine how lots of fish and crustaceans and mollusks and so on can actually defend themselves from predators by just hiding between the branches of this beautiful coral. And given this fantastic sheltering, not only from predators, but also from UV light from the sun, which is very damaging, especially to tiny little fish when they're juvenile, it can extend to the kilometer scale, as I mentioned about the Great Barrier Reef, but there are very many other reefs that extend at least at the meter scale, most frequently hundreds of meters, and in a few places, kilometers. So all coral skeletons are spherulitic, not only Stylophora, the one I showed you before. Here we have Porites and Stylophora, the one I compared earlier. You see that here we have the centers of calcification. In this case, we see the radial distribution. Here we don't. Here we see this spherulitic structure from a side. Here we see centrally. Here we see from a side again, and you see the centers of calcification that extend approximately following my mouse and this way. And you can see that it's the centers from which all of these radial distributions begin. So you can see the radial distribution on this side like this, and on that side like that, and so on. So the centers of calcification are always along lines, and these lines don't have to be straight. They can actually be quite tortuous, as in these two cases. These are more corals, more spherulites. As you can see, this is in Balanophilia, this is in Acropora. You can see that the radial structure here, and then we see something new. Here at the growth front of this spherulitic structure, we see something we haven't seen before. This we call sprinkles because in a PIC map, they actually look like sprinkles on a cupcake or on a birthday cake that are all tiny, very colored, and they have no correlation with the orientation of the crystal surrounding them. So they're really tiny, completely misoriented sprinkles, and in PIC mapping, they look colored because they're oriented differently. I should have said that color in PIC mapping represents orientation of the crystals. It was probably obvious from what I said, but this color bar in all of the slides I showed earlier represents the C-axis that comes out of that hexagonal prism crystal habit. And if it is vertical, it's cyan. If it's horizontal, it's red, and every color in between. So in this case, we're looking at Acropora, where we see that these sprinkles, so these randomly colored tiny little crystals, are actually localized at the centers of calcification. We looked at more than a dozen species and phyla, and genera, and we found that only in Acropora they localize at the center of calcification. In Balanophilia, they localize at the growth front of the spherulites, and you can see one line there, another line at another growth front there, and then another one a little more confused there, and this is the outer edge of the skeleton. So because I do have a couple of minutes, I would like to explain that. The way spherulites form, we actually discovered from this type of images. The fact that there is growth front nucleation or randomly oriented crystals that we call the sprinkles, these very colorful different little sugar sprinkles. And then if those that are randomly oriented, they can have any orientation that's random. But if they are oriented with their c-axis, let's call it tangential, if they're along a circumference on this, if this is a center, this is a circle, if they're tangential to that circle, then they're gonna run into each other and they can't grow big because they bump into each other, they have no more space to grow. If they're oriented radially instead, they have plenty of space to grow. And this is great because this is what's gonna form spherulites. And in fact, you see that in the case of Acropora, where they are very much accumulated at the centers of calcification, they actually always radiate there. So this is obviously a green sprinkle that didn't grow. This magenta sprinkle didn't grow, this yellow sprinkle didn't grow, but then this other one here, this magenta one, had space to grow, and so it grew radially. Same for this blue one here, it went. The green one didn't have space to go because it bumped into the blue one, and so the blue one kept growing, the green stopped. So why did corals evolve to form spherulites? What's so special about spherulites? Well, I described to you how spherulites grow, not only in coral skeletons, they actually grow in all sorts of organic polymers, in a lot of pharmaceuticals. For example, aspirin, when you take an aspirin, it has to be crystalline because that way it has a much longer shelf life. And because, and spherulites are the favorite structure for crystals in the pharmaceutical industry because they're very easy to see under the optical microscope. So they don't even need to do X-ray diffraction. It's much faster to just look at them, even wet, under an optical microscope between two glass slides. You see this beautiful radial distribution, you know your aspirin has crystallized. Not only aspirin, a variety, an enormous number of different pharmaceuticals, as well as chocolate, sugar, all sorts of things in all sorts of industries. So spherulites discovered how they form from coral skeletons are actually important in a variety of different systems. But let me get back to the question, why spherulites for coral skeletons? And the answer may be that material properties are better along the c-axis than along the A and B axis. I mentioned that these needle-like crystals in a spherulite grow along the c-axis. Aragonite always grows preferentially along the c-axis like a needle. And interestingly, if you look at the mechanical properties, they're all better along the c-axis than across. So if you do an indentation experiment along the c-axis, imagine my finger is an aragonite crystal. If you do an indentation experiment along the c-axis, or if you do it perpendicular to the c-axis, you'll find that all of the materials properties are better along. So the hardness, the stiffness, the yield strength, the tensile strength, the toughness, which is resistance to fracture, they are all much better this way than that way. So building coral skeletons spherulitically is a tremendous advantage. Why? Because if a spherulite always only grows along the c-axis, it means that they're all c-axis. And so, first of all, a single crystal of aragonite is strongly anisotropic. It's very different along the c-axis than along A and B. Whereas a coral skeleton, which is all spherulitic, is perfectly isotropic. Plus, it's harder, stiffer, stronger, and tougher. So there's an obvious evolutionary advantage for the animal to build a spherolytic structure compared to any other structure. And that's why the spherolytic structure of coral skeletons makes it possible to build entire reefs from the nanometer to the kilometer scale. Not only in corals, but many other biominerals have the same slight misorientation of adjacent crystals that we see in a radial distribution of C-axis, which we've already seen in the centers of calcification and radiating from there in coral skeletons. But it's also true in butterite spicules from a tunicate ascidian that you can see here. That's the approximate location, not to scale. That's the approximate location of this pick map. That's the approximate location of this pick map. And on the outside, in calcite, on the outside of Pinctada margaritifera shells, you see this is a mollusk seashell. You see that the adjacent crystals are always only slightly misoriented. And again, for aragonite and butterite, the C-axis is represented by color. For calcite, the C-axis orientation is represented by color. The crystal habit is rhombohedral, is not hexagonal or pseudo-hexagonal prisms like in aragonite and butterite, but the concept is the same and the color scheme is the same. So for all of them and more, for nacre, which is mother of pearl, on the inside of abalone shell or Pinctada shell, or even in an ancient Atrina shell, 13 million year old, we see columnar nacre, sheet nacre that has these columns of co-oriented aragonite tablets, staggered diagonally in sheet nacre from bivalve mollusks. And this is another bivalve mollusk, although a fossil is just a fragment. And as you can see, it's still iridescent, it's still beautiful like a pearl. And it has these diagonal stacks of co-oriented tablets. So fantastic. We see that adjacent tablets are very closely colored. You see that the colors don't change very much. And if we measure that quantitatively, we see that diverse biominerals have slight misorientation of adjacent crystals. And by slight misorientation, I mean between 1 and 40 degree misorientation. So if we select two regions, like here, J1 and J2, G1 and G2, B1 and B2, A1 and A2, and or here, B1 and B2, I1 and I2, and so on and so forth for all these systems, we see that we have always very small misorientation. We have huge statistics on this observation. We see it in synthetic spherolites, we see in natural spherolites, we see it in coral skeleton, in nacre spherolites, and so on. Here we have it across 6 completely different types of mollusk shells that form nacre. And they all invariably have this small distribution. You see, I plotted not from 0 to 90 degrees on the horizontal axis, because absolutely nothing happens after 40 degrees. There are no points. And so I just cut off the range to restrict it to 40 degrees. And we see that for butterite, we have a few points at higher angle, but always within 40 degrees. And for calcite, same story. So for very many different biominerals, we see these slight misorientations. Is it useful? Does it improve a material property? And the answer is very much yes. We did a molecular dynamic simulations with my brilliant collaborator, Marcus Buehler at MIT, and his fantastic student, Andrew Liu, who also just defended and became a doctor. So they did Andrew did MD simulations with 2 crystals. Let me run the simulations again because they're so cool. So there are 2 crystals here. At the interface, there is a misorientation of a slight angle here, only 10 degrees. Here is 0 misorientation. This is basically a single crystal, and 45 degree misorientation. And you see that when a crack starts from the notch on the left, then it propagates. Let me go back one so you can see it again. Starts from the notch, propagates through. When it gets to the interface, it's deflected. And it's deflected a lot more with small angles than with bigger angles. And that's a bit surprising. We don't fully understand this, but we observe it systematically. We tried it with all sorts of angles of misorientation. We tried it with aragonite, with baterite, with calcite, and in molecular dynamic simulations. We always find a maximum at small angles, as you can see. Therefore, slight misorientation in coral skeletons makes it possible, makes the coral skeletons tougher, and this contributes to the coral skeleton's evolutionary success and formation of the entire reef ecosystem, which you can see extends to the large scale. And that's due to the 3D structure, which is due to the spherulitic arrangement. With this, I'd like to thank my fantastic group that's getting bigger and bigger every day, and it frightens me, and splendid collaborators, especially Sylvie Tamboutet, who's the director of the Centre Scientifique de Monaco in Monte Carlo, and her husband, Eric Tamboutet, who provide me with all of the corals, Talinas, that accompanied me on this wonderful endeavor at the beginning on coral skeleton. All three of them are marine biologists and world experts on coral skeleton formation, and lots of other people that I am privileged to collaborate with. And finally, I thank you for your attention.
Oh, thank you very much, Embarked. A very, very nice presentation, and you can see that people are.
Thank you.
That's very nice. So, I would like people who have a questions, because I've not seen people drop it, but I know that Simon was saying something like how this research can help us protect our coral heritage. That he wonder how did. All right. So, the only thing that is, let me just ask. There's one question I want to ask, which fine, I might be corrected. You said all coral skeletons are spherulite.
Yes.
You put all, the word all. Is it all? Does that mean there is no one can be a spherulite?
I'm sorry, can you repeat the question? You were breaking out, so I didn't catch it.
Yeah, I can type it. You said all coral skeletons are spherulite. I was trying that. Does that mean no one can behave in another version? So all of them are spherulite.
Yes, and they are randomly oriented, and this is one spherulite, and this is another spherulite, and that's another spherulite, and they fill three-dimensional space with no holes. If we do an experiment that's called BET, Brown Hour Emmett Teller, we actually see that they do form one nanoparticle at a time, but they fill space completely, just like a single crystal of aragonite or a single crystal of geologic calcite. They show the same BET measurement, which is on the order of 1 to 10 square meters per gram of powder. This is the surface area measured with BET. And it's very, very similar between 1 and 10 square meters per gram of powder, which is comparable to the geologic system, the geologic single crystals. If you compare with nanoparticles grown in the laboratory that are of similar size, those sizes are actually something like 300 square meters, not 1 to 10, 300. So it's a lot bigger. The surface of nanoparticles is enormous.
Okay, there's a question on the Lawrence is coming. Can you attempt a question in the chat? There's a question for you in the chat.
Yeah, so Simon asks, how can this research help protect the corals? So there are two things. One is that with the research that I showed a little bit from Connor Schmidt, my brilliant student, that shows the amorphous precursors on the surface. Remember that the amorphous layer on the surface was different for the different genera. And in particular, our research thus far, we've only studied these three, but we've shown that they are very different from each other in thickness. What that means, because we've analyzed all of them exactly the same amount of time after the death of the animal, 24 hours after the death of the animal. That's how long it takes us to prepare the sample. Because they're all identical in preparation, then we can conclude that the crystallization rate is different. Remember that these amorphous or amorphous minerals are precursors to aragonite. And so a thicker layer indicates a slower crystallization rate. A thinner layer indicates a faster crystallization rate. So the more, we've also correlated this thickness of amorphous layer with the resilience to ocean acidification, which can be tested in aquaria. And we've seen that the thinner the layer, the more resistant it is to ocean acidification. So for example, Acropora gave the thickest layer of amorphous, meaning that it's slower crystallization. And what that means is that this is not a resilient coral, which is bad news, because all of the programs for reintroduction of corals invariably use Acropora because it's such a beautiful coral, it's branching, it's widespread all over the tropical world, and people reintroduce that preferentially because it's so abundant. Bad idea, because by 2050, ocean acidification will be bad enough that it will dissolve and die. All skeletons will dissolve and the animals will die. Many other corals do survive ocean acidification, Acropora does not. So choosing the right species is the way to the future. There are also other more applied interventions that I can tell you later.
There's a lot of questions here, I know. Try to look at another question there.
So other chemicals that can contribute to beautiful colors? Well, yeah, so the colors are a complete artifact, actually. It's just a way to display the different chemicals, and it's under review right now, and so it's not published, but I've actually come up with a method to display more than 3. You can do it with any chemical. The beautiful introduction that Jihan Kamel just gave us to infrared and microspectroscopy, you can do it at the nanoscale, you can do it at the galactic scale, you can do it at the atomic scale. When you have a lot of different chemicals, you can actually map a myriad of them with this new method that in fact I call myriad mapping, because I want to highlight that we can actually image very many. Thus far, we've been limited to 3 because red, green, and blue, or cyan, magenta, and yellow maps is all computers can handle. But with myriad mapping, we'll be able to display many, many more.
Okay.
No, I don't have any.
Another question before Lawrence.
I don't have any collaborations with Africa, with anybody in Africa. If you guys want to collaborate, please come and do experiment with me and invite me to come to Africa. I would love to come. Yes.
We got to do that. Okay, Lawrence.
Oh, yeah. You have my book.
Lawrence, over to you. Can you open your, Lawrence? Try to.
Lawrence, you're muted.
Unmute yourself. You are muted.
Okay, sorry, I just wanted to show the book, and so we can go on to the next speaker.
All right. Thank you very much, Gilbert, and I hope that after this conference, don't worry, we'll receive a lot of interesting email for the collaboration. All right. Our next speaker is Professor Rebecca Messler. Going to talk about using AfPS and to exploit barnacle exoskeleton and astrology and astronomy Colgate University. Now over to you, Prof.
Hi, thank you. And thank you for giving me the opportunity to share about my research. So my home university is Colgate University, but right now I'm actually very lucky to be in Cape Town at the University of Cape Town for the semester. So today I will be talking more of what kind of Pupa was just speaking about, and that delights me as Pupa was my PhD advisor. So I will be discussing XPeam and Zanes in a little bit more detail, and then in particular talking about how we can use it to learn things like information about barnacle exoskeleton formation. So for those who are not so familiar with barnacles, they come in two main forms. We have the sessile barnacle that is most of these pictures. That's the volcano-shaped organism. And then there's the stalked barnacle that is in the middle and is a little less common. Now, barnacles can be found all over the world. In visiting the many beaches around Cape Town, I see them in all the intertidal zones and on the docks. And they do adhere to all kinds of different substrates through an amazing adhesive that they produce that I won't be speaking about today. Instead, I'm going to be focusing on that hard mineral that surrounds the organism and protects the organism from environmental conditions. But I'm actually more interested not in these big barnacles that we see in these pictures, but in their early life stages. And so the barnacle, in my eyes, is much more interesting than just that adult because it has many life stages. It starts life as a free-swimming nauplius, where it can swim through the water column, eating diatoms, algae. It goes through several different stages before undergoing a metamorphosis into a cyprid. And in that cyprid stage, it has a little antennule, which is shown on the left of the cyprid image, that it uses to feel different substrates and decide where it is going to settle down for life. And that really is what happens. It sets down its little antennule, it secretes an adhesive, and then it undergoes yet another metamorphosis into this juvenile form before it matures into the adult. And as long as nothing comes and picks it up, it stays in that one location for its entire life. My research group in this particular project are interested in looking at what happens in going from the cyprid to the juvenile, and then as that juvenile matures into the adult barnacle. And we have four main questions that we are trying to answer as we look at this organism. And we do that by growing these barnacles on little silicon wafers. And that's what you can see here. So this is a newly metamorphosed barnacle, and it is sticking out its cilia to be able to eat. And you can see some cyprids that are floating past it. This silicon wafer is 10 millimeters on each side, and so you can get some kind of scale for these juveniles. They're not very big. And ideally, when we are looking at these barnacles that have just undergone metamorphosis, we have these four main questions that we would like to answer. We want to know how the exoskeleton develops. We want to think about what minerals make up the forming exoskeleton. We want to know about the structure. So how are those crystals oriented, just like what Pupa was talking about? And then how does that correspond to strength and materials properties? Now, to be able to answer all these questions, we do use a variety of techniques. So because of the length of today's talk and thinking about the synchrotron piece, I'm only going to focus on question 2 and 3, which is thinking about the minerals that make up the exoskeleton and then thinking about how those minerals are structured within that exoskeleton. And I'm going to do so by talking about a synchrotron technique that I was introduced to as a graduate student in Pupa Gilbert's lab, and that is X-ray photoemission electron microscopy. Now, to talk about XPeam, we first need to talk about X-ray absorption near-edge structure, or Zane's spectroscopy. And this technique depends on the physics that many of us know and love, where you have an atom that is hanging out in a material, you have light coming in to interact with that atom. If that light is the appropriate energy, which depends on the exact atom you're trying to probe and the environment that the atom has, what bonds the atom has, then that electron gets excited into an unoccupied bound state. Eventually, that excited electron comes down and you get either an Auger electron, which is what we measure with this technique, or a fluorescent photon. Now, Zane's spectroscopy on its own is really wonderful because it is bond specific, it is surface sensitive, and you can analyze all kinds of different materials. So you can look at organics, you can look at minerals, and then you can look at composites, which is what is really important to me because just like the corals, my barnacle exoskeletons have a mixture of organics and calcium carbonate, so that I need to be able to look at this composite material. And Zane's is a powerful technique unto itself, but when you have a non-uniform material, just like the biominerals that Pupa was talking about, and then the barnacle exoskeleton I want to look at, you need to add something else in so you can localize that information and get what you need. And that is where this X-ray photoemission electron microscopy comes into play. And so this is a schematic where you can think about that advanced light source where I do many of my experiments as that ring, and that's the synchrotron that we are going to be thinking about in this, where you get light from it, it interacts with the monochromator to get your particular energy you're interested in. That light is incident on a sample that is held at -20 kilovolts, and that -20 kilovolts then makes it so those excited electrons go down the electron optics to a phosphor screen and eventually form an image on your computer. And as we build the Zane spectrum now, we are taking an image at every single energy. And so you get a stack of images that make a movie. And from every single pixel in that movie, you can now extract a Zane spectrum, which means that you now have chemical environment information with a spatial resolution of approximately 10 nanometers if you have a really amazing sample. Most of my samples are a little less amazing than maybe will get you that kind of a resolution. So what does that mean for my samples? And to be able to look at them in the synchrotron, we have to first take a view of what a juvenile barnacle might look like. So this is an example of a 2-day post-metamorphosis barnacle, just looking at it in a scanning electron microscope. And these exoskeletons have 2 main plates that we have to think about. There are the parietal plates that surround the organism. And then there are the opercular plates that actually are what open and close to allow that organism to eat and filter feed. And to be able to look at them and be able to get the kind of structural information we want from XPEAM, we actually take these little barnacles, embed them in epoxy, and polish them down to a cross-section so that we can then look at them in the synchrotron. And if you're looking at a cross-section, and this is an example of a 6-day-old barnacle, you would see something like this, where now the parietal plates form a ring around the outside, and you have the opercular plates on the inside. And so that's what I want you to have in mind as we start to go through some of this PEAM data. So from PEAM, as Pupa was saying, you can get all kinds of different information. And one piece of information that is interesting when you're looking at biominerals is calcium for calcium carbonates. And in my graph here of the calcium L-edge, you have a calcite, geologic calcite spectrum on the bottom. That is in black. And then we have spectra that I acquired from the parietal plates of the 6-day-old barnacle and the 1-day-old barnacle in blue. And one thing to notice right away is that all of those spectra look alike. So all of these are showing calcite. And so we can take from that our barnacles at this young age have calcite in their forming exoskeleton. To the left are images of these barnacles that were taken by dividing an image acquired at the peak of our calcium L-edge spectrum by an off peak. And so what that does is really highlight the calcium within our sample. And you can see in our 1-day post-metamorphosis barnacle, parietal and opercular plates, one, they are thinner than the 6-day-old, which is expected, it's young, it's just formed, and it is not as smooth of a texture. And so you have some clumping of this concentration of calcium, which is an interesting process that we can think about. So that tells us a little bit about the mineralogy. But once again, we also wanted to know about the structure. And so that's where we go to this PIC mapping that Pupa was talking about. And so just a kind of brief overview of how this works. You have the C-axis of your calcium carbonate crystal. If it's aligned with the polarization vector, then you get this nice pi star peak at the oxygen K edge, and the sigma star goes down. If you then change the orientation of your crystal so it's perpendicular, you get those flipped. And Pupa's group has really took this and just made it into a beautiful mapping that you're going to be able to then see all of the different orientations of those crystals with color. And so now each of the different colors represents a different orientation, C-axis orientation relative to the polarization. So for our barnacles, this is what we see. And so once again, these are the same areas that I showed you before, but now with the PIC mapping and the colors. And you can see that the 1 day post-metamorphosis is thin. You see that the colors match up with where the calcium was. And you see very small grains. So you see different colors that are in small kind of proportions, and that they are rather random. So you don't have co-orientation of these crystals. Instead, you have a lot of different colors that you were seeing. By the time you get to the 6-day-old barnacle, you still see a fair amount of coloration, so a lot of different orientations. But now you start to see larger crystalline domains. And so we can start to think about what happens in that process of going from 1 day to 6 days for that barnacle. Now, there is a lot more that I could tell you about each of these different things. But one last thing I want to kind of show is the power that you can just start to build up a map of all of these different regions. And for an organism as small as a juvenile barnacle, you can actually almost map the entire organism. So you can start to see what trends you are having. And that allows us to start building up models of what is happening and how this organism is developing its exoskeleton. So I'm going to leave it there because I was told to do 10 minutes and give you a few quick conclusions and say that we're doing a lot more than that, but I'm happy to answer questions after a moment. So just from what I've told you here, we can talk about the composition, and we know that calcite is forming within that first day following metamorphosis. We know that these crystals are small and randomly shaped and oriented, and that they become larger crystalline domains with age. My lab is also doing a lot of work looking at the environmental impact as we think about climate change, so looking at different temperature, pH, and combination of those two. And of course, I want to acknowledge all the people that have been a part of this project. Colgate University is an undergraduate institution in the United States, and so I do all my research with undergraduates. They're shown here following our synchrotron time in California. And then I have collaborators at the College of New Jersey, Duke, and Cornell that also help me with this work. And then the National Science Foundation for funding what we have done. And then, of course, Pupa's group for distributing the macros that allow us to do the analysis for each of these. So I'll end there and I will answer questions. And I see.
Let me just ask a quick question. Are you collaborating with a group at UCT, or you're just on holiday?
No, so I have been working at the electron microscope facility and have been in the physics department for the term. Yeah.
Gotcha. Okay, great. Thank you.
But as with Pupa, I'd be happy to collaborate with others who are interested in these kinds of questions. Yeah.
All right.
I have a question, if I can. Can I ask a question?
Yeah.
So are there any amorphous precursors? And have you thought about the process of coarsening of those small crystals that become bigger crystals with aging and with growth of the barnacle wall, parietal wall? And this would actually, it could occur either by a solid state transformation or by dissolution or reprecipitation. It doesn't really matter, but the effect is that small crystals grow bigger. And typically, that's exactly the same thing that happens with spherulites.
Yeah, it's a great question. So we have not yet detected any amorphous precursors, and that's both with PEAM and then what I didn't talk about or show is that we are also doing Raman spectroscopy with Lara Estroff's group at Cornell on live barnacles. And even with our live barnacles, we've not detected amorphous precursors. The first thing that we find is calcite. So we're still searching, but we haven't found any hint yet of amorphous precursors. And then we have been thinking about coarsening and trying to think about ways that we could ensure that, like, figure out whether that's exactly what's happening or if there might be something else that's going on. But yes, that is what is coming to mind as well.
I have a question.
Thank you.
I have a question.
Okay, yeah, that's the last question because we need to go by table, right?
No, I say I have a question on the chat.
Oh, on the chat.
Yeah, yeah.
Oh, so no, I am not talking about corals. So barnacles are a different organism than corals, and they are in the intertidal zone instead. And yeah, so they also make biominerals, but a different organism altogether.
It is because we don't understand what kind of things you are talking about. Maybe you can explain a little bit.
Yeah. So I'll go back to the slide. Hang on, let me find it.
But we are not specialists of this question.
What was that?
Could you explain a little bit
About what barnacles are?
Oh, about what you are talking about?
Yeah, what's the difference between a barnacle and a coral? That's the
Yeah, totally. Okay, so I don't have a slide that shows that very well. So when we're talking about there are all kinds of different organisms that make biominerals. And when we're talking about biominerals, we're talking about materials that are a mixture of organic and inorganic. So the ones that we think of and that we're very familiar with are our bones, our teeth, right? Those are the ones that we have in our bodies. However, marine organisms produce a variety of biominerals. And so Pupa talked about a number of them. So there are like abalone shells. Those are organisms that have that iridescent mother of pearl. That's kind of the tablets that you see. Then there are the coral, and I think a lot of people picture corals when they're thinking about biominerals because they're always in the news, they're beautiful and stuff like that. And then the barnacle is what I was showing at the beginning, where you have these kind of volcano-shaped organisms, and you'll find them on ships, on the bottom of ships, you'll find them on rocks in the shores. So those are the ones that I was talking about for this talk, but there are there's clams that have those shells. So anything that makes one of those kinds of shells, that's a biomineral, but we classify them by the kinds of biominerals that they make. Does that help?
Yes, because at the beginning of your talk, it seemed to me that I have seen some insect. Yes,
yeah.
After there is something else.
Yeah, so that's a great, so the barnacle is strange in that it is a crustacean. So it has a different form when it starts its life, and then it undergoes metamorphosis to become that kind of volcano-shaped organism. It's all one organism, it's just different life stages that are very, very different from each other. So unlike humans, where we go from baby to like an adult and look pretty much like a human the whole time, these organisms have drastic changes in their morphology.
Okay, thank you.
They're all calcium based, right? So is there like a lead-based barnacle or a lead-based coral or some other group to the metal that
there's silicon. There are the silicates that you can think about. No, I don't know of anything with lead.
Okay.
Yeah. All right. Thank you, colleagues. I think I'd like to thank all the speakers. We really appreciate their talk. Very interesting. And I believe we can take it offline, because that's why we ask all the speakers to do their email, their contact details.
Okay.
To make some inquiries. And if you look at the program now, we need to have what we refer to as a break, and we're trying to spend most of the time for that, but maybe we can just have a 5 minutes before we can be able to come in breaks that we can be able to start the session. Because I'm trying to find a way where we can be able to at least just find a coffee. I know we are in our respective places. So according to the program, we have to just have it's supposed to be 10 minutes, just 5 minutes, then we can be starting. Lawrence, are you okay with that? 5 minutes?
Yeah, that's fine. Let me make sure that the speakers are here.
Oh, okay.
That's Anne, right?
Yes, that's me. I'm here.
There you go. And
nice to see Anne.
Mona I did see her earlier. Okay.
Amazing.
All right, we're good. So let's I don't know, 5-10 minutes?
Yeah, fine.
Okay.
All right. Yes.
Cheers, thanks.
5-minute break.
Yeah. Okay. So people, I do have your book. I have used it.
Thank you. How kind you are.
Yeah, it's a little worn. I've used it several times. But yeah, it's a good book. And there's one called the Physics of Plays or something. The Physics of Theater. I don't know if you've seen that one.
Uh-huh.
But
No, I have not.
You used them together.
Oh, I see. Okay.
I
haven't seen it.
There was a production of the Fantastics a few years ago in Washington, D.C. that used a lot of optical effects.
Uh-huh.
The Fantastics being one of the oldest Christmas plays there is.
I see. Cool.
Yeah. Well, thank you for attending. So you're like on a sabbatical at Berkeley these days?
No, actually, I live here with my husband, and I have all of my experiments at the Advanced Light Source, which is based in Berkeley. So I'm done with my 2 months of teaching, the first half of this semester, and the second half, another professor is teaching the rest of the course, and so I can be here and do research. So I'm doing very intense research these days.
Oh, cool! All right. Fantastic.
Yeah, exactly. I love this lifestyle of spending 2 months here, 2 months there. It's just the perfect rhythm.
Yeah.
How
on
you?
Multiple levels, I'm sure.
Yeah. Do you live in the same place all the time?
I live in Washington, D.C., and so.
Oh, I see. Oh, I thought you were based in South Africa. You're not based in South Africa.
Sort of a workstation somewhere else sometimes.
I see. Okay. Are you a synchronous scientist?
More theory. I do more theory than
I see. Fantastic.
But yeah, I guess you did mention that people can do experiments with you, and there's a program, the LAMP program, which I guess there'll be a talk on. I guess we have to move that talk to tomorrow. But there's a process, a funding mechanism that we have for people to. I think it has to be a faculty and student team.
Fantastic.
But these days, I mean, just getting the visa is half the battle. It's more than half the battle.
Oh, I'm super sorry about that. So for me, the battle is to get beam time because it's super competitive. On the beam spectrum microscope, it's oversubscribed by a factor of 5. So, it's only 20% of the applications go through. And so you have to be insanely competitive. Right. Recently, I discovered this mechanism they have at the Advanced Light Source called the approved program that gives me something like 5 or 7% of the available beam time, which is a lot. It's a lot more than I can get as a general user, where the limit is 3 or 4% of the available beam time if you're the top scorer. And but it costs a lot of money because I have to contribute money for the salary of a person or a big piece of equipment or something. And so this time I just put in a lot of money to support a beamline scientist. And so I hope I get it. But my proposal is currently submitted. So I currently have one for 3 years, but it should be renewed for another 3 years if I'm lucky. So it's not like I have been time to waste, but of course, I am very happy to collaborate with people from Africa. And especially if people are happy to write proposals for beam time, then we can actually get beam time, and I can help with the sample preparation, with the designing of the experiment, with the data taking, with the data interpretation, data processing. I actually distribute the software for processing beam data for free on my website, and you can just download it. It runs in Igor, and then you can do pick mapping, you can do component mapping, you can do a new thing that's called Pelican that is not there yet, but it will be there soon before the end of this year. And so, and then I'll be able to do myriad mapping sometime very soon, so as soon as the paper is published. So at least from the software point of view, I'm sharing a tremendous amount. And there are several people around the world, about on the order of 20, 30 groups that actually use it all the time, because I get email from them with requests and clarifications and things. So yeah.
Now, can people send samples to the beamline and sort of remote? No. So you have to come. No. You have to bring yourself with the sample.
Well, so if they get beam time, I'm happy to use their beam time and process their sample. And I have a big group. I don't have any trouble doing this. So yes, if you want to get around the visa problem, yes. If you want to get around the applying for beam time, no.
Gotcha. Okay.
I am not going to use my beam time to do someone else's experiment. I'm sorry. It's too precious. So if people want to write their own proposals, I'm very happy to help. And if they can't come because of visa problems, I'm very happy to help and run their beam time. No problem.
Understood. Okay, thanks.
Let me just do a little bit of clarification. Hi, my name is Sekazi Mtingwa, and I'm chair of the LAMP program, which sends people for training. So the idea is for them not to necessarily apply for beam time. The idea is for them to go and learn by assisting whatever you're doing. Whatever the beamline scientists or whatever experiments are running, they can kind of assist with that just to learn their way around so that they will be in a position to start writing their own proposals. So we're taking people who have absolutely no experience with synchrotrons in the past. And so that's sort of the idea.
That is fantastic.
Yeah, okay.
But first of all, nice to meet you, Sekazi Mtingwa. I love your idea. Nice to meet you. I love this idea. It's the best idea I've ever heard. Out of any country, out of any continent. This is exactly what the world of synchrotron needs, because what we do is insanely complicated. And the fact that I actually have to pay for people to actually look at what's happening is ridiculous. Because then I have to put a lot of money and I had to spend a lot of time during beam time when I'm under pressure to produce as much as possible in a very short amount of time. This is my teaching time. This is insane, right? I want to focus on the experiment. So sending somebody as an observer that's paid from LAMP is a brilliant idea. Congratulations. You're doing the best. And yes, send me people. Send me people. Send me people. I have beam time November 30th to December 4th. Can you kindly send me somebody?
Okay, we'll look into it. Okay, thank you so
fantastic.
Much. Thank you. Good luck.
You're welcome.
Simon, I don't know who the chair of this session is.
I thought Philip could just continue because the chair has not showed up. Philip, can you continue?
All right. Welcome everyone, and I'll still be the person that will be sharing this session again. Philip is my name. So I believe based on the time, because we need to find a way to get back our times table again together. And then our next speaker will be Professor Anna Lena Roland. So she'll be talking about how can countries of the Global South get a fair deal out of membership and participation in big science projects. So over to you, Prof. Roland.
Thank you for the introduction, Philip. I will quickly share my slides, and it would be great if someone could let me know that you actually see them.
Yeah.
You see my slides?
We see them.
Great. Yeah. And I apologize in advance if you hear some background noises. We currently entered the stormy season in Leiden, so there's a lot of wind and rain. But yeah, good afternoon, everyone. I'm Annalena. I'm actually a PhD student at Leiden University, writing a PhD thesis on stakeholder interests and conflicts in big science. And I'm excited to be here. And I would like to thank the conference organizers for having us. I'm saying us here because I'm presenting on behalf of my colleagues. That would be Nicolas Ruffin, Katharina Kramer, Manoj Saxena, Prosper Nganbonzica, and Stefan Skupin, some of which are also in the chair right now. And together with my colleagues, I wrote a paper, or the paper on which this presentation builds. And I really can't stress enough that that paper has been a truly collaborative effort, which hugely profited from the complementary skill sets and expertise of the involved co-authors. Now, having said that, let me jump right into the presentation, as we would like to have about maybe 10 to 15 minutes for a hopefully lively discussion with the audience. And what initially prompted my colleagues and me to conduct a study on the role of the Global South in big science was several recent developments in the broader big science landscape that we observed in the last few years or so. And what we first saw was that an older generation of big science in the global north, for example, CERN, becomes increasingly internationalized. And then second, we observe the emergence of a new generation of big science projects in world regions, where until recently no or very few of these projects existed. And Sesame, that was presented in a previous session, is actually a case in point here. But in both types of big science, we see emerging powers of the global south, like, for example, India, China, like South Africa, taking on an increasingly active role. But at the same time, we have little social science research on the global south and big science. And that's really where our paper comes in. And that's a blind spot in the literature that we wanted to address with our study. Now, two research questions guided our project. So first, we wanted to understand what objectives emerging powers of the global south pursue in big science. And second, we aim to identify conditions under which these powers are more likely to achieve their objectives in big science. And while I will outline findings for both questions, I will spend more time discussing our findings regarding question 2, because we think these findings have the most implications for policymaking, and hopefully we can draw some lessons learned from these findings. Now, to answer our two research questions, we conducted a comparative analysis of the participation of Southern emerging powers in 4 big science collaborations. First of all, we looked at CERN. Second, we investigated ITER. We also looked into SKA. And last but certainly not least, we looked into the African light source. And with exception of the African light source, we focused on the participation of a single country in each one of these big science collaborations. Now, in the cases of CERN, ITER, and SKA, we analyzed the participation of India and South Africa, and we particularly focused on 2 phases in the life cycle of these projects. First, we examined the initiation of a collaboration, and I think what's really important to notice is that in this early phase, we don't really have any institutional rules yet, and we also don't have a governance system. But second, we also looked at the development phase of all of these projects. And in this later phase, in a big science collaboration, we have institutional rules, and there's also a governance system in place. In this context, the African light source is a bit of an exception again, because as you all know, it's currently still in the planning phase. So we only examined the initiation of this project in our paper. But for the description and analysis of all our 4 case studies, we combined a document analysis. So we were looking into newspaper articles, policy papers on the projects, but also the academic literature. And we conducted a few qualitative interviews with scientists and managers at the big science collaborations that we looked at. Now, let me come to our findings and start off with our first case study. That would be CERN. And you're probably all fairly familiar with the collaboration, but I think it can't hurt to just recap that it's a collaboration in high energy physics. It was founded in 1954, and its governance was and continues to be dominated by its European founding members. And that's mostly because CERN has a quite rigid institutional framework, and said framework hasn't changed much since CERN's initiation. But eventually, over time, the need for bigger and costly instruments in high energy physics, we have, for example, the Large Hadron Collider, which is a really expensive, big project, enabled non-founding members to take on a more prominent role in the overall CERN project. And so what they did effectively was that they traded their financial contributions to projects like the LHC to have a bigger say in CERN. I think India's involvement in CERN illustrates this latter point quite well. So the country's motivation to join LHC was threefold. First, it wanted, or it saw the LHC as an opportunity to strengthen its national high energy physics program. Second, India viewed the CERN and LHC as an opportunity to showcase the capacities in science and technology that it already had. And third, since some of its regional rivals, for example, Pakistan, had become increasingly involved in CERN, India was motivated to participate to kind of cement its image as a powerhouse of science and technology. In the long term, that strategy really paid off, but the emphasis here needs to be on the long term, because while the country was granted observer status in CERN during the construction phase of LHC, it took another 15 years for India to become a CERN associate member, which is seen to be a status that comes with a lot of political prestige for the country. And although these types of extensions of membership types within CERN were useful for countries like India, they didn't change much of the overall governance at CERN. So currently we only have 3 European states in pre-stage to full membership, but there are no states from the Global South that are in this stage in CERN. Now, let me continue with our case study of ITER. ITER is a big science collaboration in nuclear fusion, and the international organization which oversees the construction of the nuclear fusion reactor, which ITER ultimately is, that's currently underway in France. Cadarache was established in 2007, but the roots of the project go back all the way to the 1980s. And India was the last country to join ITER, but it still had considerable capacity to determine some key institutional features of the project, because when it joins, meaning
said I'll see you tomorrow.
Parties that are the US, Russia, South Korea, China, and the EU, they hadn't agreed on an institutional framework yet. So that was beneficial for India, but at the same time, the country didn't have any say when it came to the scientific objectives of the collaboration, because that was already settled before it joined ITER. But I think it's also important to know that India had 2 main motivations in case of ITER to join. First, it wanted, and I think that's the parallel to CERN, strengthen its capacities in fusion research. But second, and I think that's quite interesting, it was keen to join ITER because it wanted to reestablish itself as a trustworthy nuclear power after it had refused to sign the Nuclear Non-Proliferation Treaty in the main 70s and kind of got ostracized by other nuclear powers. In theory, the institutional setup of ITER allows India to pursue these 2 objectives, but to a certain degree, the country kind of self-sabotages itself within ITER because it doesn't second sufficient personnel to ITER. And that makes it difficult for India to have this knowledge transfer between the construction site in France and then its nuclear fusion community in India. On the other hand, India, as the US, doesn't provide its full in-cash contributions to ITER, which, as you can imagine, leads to ill will among the remaining partners. They have to accept project delays and chip in more money to make up for the lacking funds. In our third case study, we looked at SKA, a big science collaboration in radio astronomy. I think you're all certainly very familiar with it, given that part of it is currently under construction on the African continent or has already been constructed. Let me just quickly recap that the international organization which oversees the construction of the project was founded in 2019. The earliest deliberations for the telescope, or one kind of big telescope project, started in the 1980s, however, and among the founding members of the SKA currently are the UK, the Netherlands, China, Portugal, South Africa, and Australia. On the African continent, it's particularly South Africa that takes on a prominent role in SKA. The country got involved in the early deliberations for the project in the 1980s. And already at that point in time, South Africa's radio astronomy community proposed and worked towards hosting SKA. And then following the fall of the apartheid regime in the mid-90s, the community was backed up by the country's Ministry of Science and Technology. Both the ministry and the radio astronomy community of the country were aware that due to its unique location in the Southern Hemisphere, South Africa really had an advantage in the siting competition for SKA. And they also saw the project as an opportunity, similar to India, to develop national science and technology skills, and then to reconnect with the regional, international scientific and political communities after decades of relative isolation. So to prevail in the siting competition, which got pretty fierce at some point, the country built up a significant capacity in radio astronomy, and that paid off in the long run because eventually it was picked as one of 2 co-hosts of SKA, the other host being Australia. And given that it is a co-host and also a major funder of SKA, South Africa has a considerable or had a considerable influence on the institutional setup of SKA, which will benefit it in the long run because it will get contracts and so forth for the project. Now, last but certainly not least, we also looked at the initiation phase of the African light source in our analysis. And from our interviews and document analysis, we learned that there are 2 main motivations for the establishment of an African light source. First, such a light source could help advance African research agendas and capacity building. Second, it would decrease Africa's scientific and technological dependency on other light sources, which are mainly based in the global north and thus harder to access. And currently, it's particularly the African research community, but also the scientific diaspora, which promotes the African light source as a project, quote unquote, by the community for the community, which kind of indicates this team spirit of the project, but also that whichever states or communities will participate or fund the project will also get a considerable say in its governance and setup. But ultimately, of course, it remains to be seen if this kind of team spirit will prevail during the usually quite contentious siting and funding negotiations of a big science collaboration. Now, in the last part of the presentation, I think that might be quite interesting for you. I would like to draw some lessons learned from our case studies and implications for policymaking. With respect to the former, I think there are 4 key lessons we can draw from our analysis. So first, our study indicates that countries can leverage their in-kind and in-cash contributions to take on a stronger role in a big science collaboration, especially of an older generation. We have seen this, or I've kind of argued this in the presentation for the case of CERN, where the need for ever bigger and more expensive instrument in the higher energy physics field kind of opened a window of opportunity for non-founding members to get more involved in the collaboration. And second, our study demonstrates that an active and outspoken scientific community and or scientific diaspora are often a pre-requirement for a country to get involved in a big science collaboration in the first place. So for example, both in the case of the African light source and SKA, participation was championed by the scientific community and or the scientific diaspora. And third, we found that strong industrial capacities are needed to take on the procurement contracts for the very big infrastructures that many big science collaborations rely on. We haven't really made that always explicit in our study, but this is really something we found throughout all of the cases that we looked into. And fourth, our study indicates that if a big science collaboration has strict geographic requirements, for example, in the field of radio astronomy, countries that meet said requirements can use their location as a kind of leverage in the negotiations. And yeah, for example, we see this in the case of SKA, where South Africa was first considered as a serious site contender because of its unique location in the Southern Hemisphere and the kind of astronomical observations that would guarantee. Finally, our study also has some implications for policymaking. First, it indicates that the institutional maturity, so how old a collaboration is, conditions what objectives, especially newcomer countries, can pursue. From our case studies, we can infer that if the goal is to take on a leadership position in a big science collaboration, then countries are really well advised to get involved as early as possible, because then they have a greater chance of actively shaping and forming a collaboration and its governance. However, if the goal is more to strengthen capacities in science and technology, countries can also join a collaboration at a later point in time, because even if the governance is quite rigid, as for example in the case of CERN, participating in such a big science project is very likely to expose the country's scientific community to cutting-edge research, and thus also likely to foster capacity building. Second, as countries of the Global South have to navigate investments into big science under more acute political, human resource, and economic constraints, they may benefit from strategically investing projects, so pick and choosing, so to say. They might, for example, want to prioritize collaborations in research areas in which they possess a competitive advantage. That was the case, for example, for South Africa and SKA. And to do so, of course, it may also prove useful for countries to analyze their strengths and weaknesses in science and technology, as well as their priorities in these two fields. Yeah, this was our presentation. Thanks so much for your attention. And yeah, I really welcome and look forward to any questions or comments that you might have. And I think my colleagues would also maybe like to chip in.
Thank you. Thank you very much for the presentation. Happy your insight and everything. Yeah, but I would like to see. Let me see the chat. If there's a question there, or any questions? Yeah. Okay. Simon. All right. Over to you. Yeah. Feel free.
I have a question.
Thank you so much, Anna and Katharina and all the other authors. It's a little bit depressing for me, because it means that if you didn't have some sort of niche advantage as a third world country, the barrier to entry is really huge. That's what it sounds like you've said. I mean, I've really picked it up myself. If you don't have that industrial support, it's also hard. If you don't have the financial backing, it's hard. So given all of that, have you thought about what advice you give to the African light source? What are our strong points? What cards can we play the strongest?
Yeah, I think that's an excellent question. And yeah, I think you're absolutely right. There's a mix of factors that kind of need to be aligned. The stars need to be aligned, so to say, for countries to really take on a strong position, especially in these older types of big science collaborations where the frameworks are rigid, and where this is lacking, it can indeed be tricky to take on a stronger role. But I think it can still be beneficial to become involved in older types of big science, because as I said, it's really an opportunity for a research community to get exposed to this cutting edge research. And I think one advantage that we really see with the African Light Source is that there is this community spirit and a very active and outspoken community. And I think this conference is testimony to this, right? Where you really push this case and try to bring it to the policy level. And not just from this study, but also from other research projects that I have going on. I know that this is one of the first key steps for a big science project to take, that you need someone to advocate for it actively and to bring it to the next level, the policy level, to have policymakers notice it. So I think that's already a key thing that the African Light Source is actively doing. But if there are any contributions from my co-authors, please feel free to jump in or make additions. Otherwise, also I'm happy to take any other question.
Yeah, thank you, Anna-Lena, for this talk. I'm Katharina, I'm one of the co-authors, and maybe I just want to add, I totally agree what Anna-Lena said, and I wanted to add from the scientific perspective, we also have to consider that the African Light Source project is, of course, different to the other case studies, for instance, like CERN, that has a very single purpose, particle physics direction, and also for radio astronomy, where synchrotron radiation is a multidisciplinary research field. And So there may be like other directions in how it can be realized and implemented in the end.
I have a question.
Okay.
And a comment.
Right. Yeah.
Okay. For big science, I think that the problem is should not be a competition, but should be a science sharing. I take the example of fusion research, the ITER, for example. Africa should participate to the ITER project because the fusion energy is the energy for the future, and it is a clean energy with zero carbon impact. And now there is almost all the nations. There is Russia, there is America, there is Europe, there is India. Even I think that there is also Brazil, but there is not Africa. Africa should be there. Africa should be there instead of talking about a small modular nuclear reactor, which will contribute to the proliferation of radioactivity of nuclear weapons, even if I can say that. Africa, we don't need a small modular reactor, but we need to participate to the ITER project. And for that, if it is based on competition and on having money and so on, it will be impossible. This is why I think that it should be based on science sharing for the progress of all humanity. This is my contribution.
Yeah, I think that's a good point. I think that there are always kind of two dimensions to these projects. On the one hand, of course, we have the scientific community that's kind of united by these values of sharing science, advancing science, but then the politics comes in at some point, right? And I think policymakers, given the nature of politics, they also need to see tangible benefits, and that's probably where the competition comes in. They kind of need to sell this to constituencies. And I think, yeah, those are two elements that are not always in alignment and need to be navigated both by the scientific community and then probably also policymakers.
Okay.
I think we have one more question.
Okay, all right. I think I'm looking at the time we need to start, but okay, let me give Lawrence a final point.
Yeah, so years ago, I had an opportunity to talk to a Ghanaian politician about the African light source. And back then the language was, well, we hope that it's built in Ghana. And I said that one does not hope that the light source gets built in Ghana. One builds the light source in Ghana. That is the attitude that the government has to have. I mean, the person that puts up the money calls the shots, and the first person takes all the risks, and that is it's like a super reality, and that is the reality of the SKA. The interesting thing about the SKA, about scientists being involved in politics, was that the person who sold the SKA to President Mandela at the time was a PhD astronomer. He just got involved in politics, and he was a high-level official in the presidency. So we as scientists have to embed ourselves in the political structure, either formally as the gentleman I'm talking about, or informally as it being active and participating in advisory bodies.
Yeah,
So,
I think that's a key point. And I personally get approached more and more by so-called hard scientists who really see the need to acquire the skills to be able to kind of interface with policymakers and support policymaking through evidence. I think that's one side of it, of course. And then for a big science collaboration, I think that also applies. You need to kind of be able to translate the scientific benefits of the project to something that's also tangible to policymakers. And so, yeah, I personally also see that need for scientists to acquire the necessary skills to bridge that divide between science and policy making and get involved in policy making in whatever form possible.
All right. Thank you, Anna.
Thank you.
I really appreciate it. I hope we can do a good job once after the conference to follow and some other questions, other advice or suggestion I need. So, then, thank you. Then, for now, because we have to run behind the schedule, we would like to call the next speaker, that is Professor Monia Asfiri. Maybe it's talking about the African strategy of physics and applied physics from the University of Mohammed V. University. Sorry, Mohammed V. University. Professor Mona, now the floor is yours.
Thank you so much. So let me first share my screen.
Thank you.
All right, can you see my screen, right?
Yes.
Perfect. So firstly, let's say hello, everyone, and I'm very pleased to have the opportunity today to talk about the African strategy for fundamental and applied physics AfPS. So this presentation is on behalf of the AfPS organization team. And yeah, I am Munia, I'm postdoc, and I am one of the co-convener of the AfPS of the African Young Physicists Forum, YPF, one of the societal engagement working groups of AfPS. So in this talk is divided by two parts. The first part I will introduce you to the AfPS strategy, and the second part will be a discussion on the AfPS, and Dr. Kitivi Asamagan will lead this discussion. So yeah, just as we have witnessed in other regions such as Europe with their well-established strategy and initiatives like SNOMAS, the global community is witnessing the emergence of dynamic strategies that drive progress and excellence. So what is particularly noteworthy is the recent interview by our colleagues in Latin America who have successfully crafted their angular grassroots strategy for research infrastructures in high energy cosmology and astrophysics. This underscores the growing momentum and commitment to advancing scientific frontiers in these regions. And of course, the story doesn't end there. Today, I'm delegated to announce that the spirit of collaboration and determination has reached the heart of Africa. So physicists from across our continent have united to develop their very first grassroots physics strategy. So this landmark initiative signifies a significant step forward for the African physics community, demonstrating not only a shared vision, but also a commitment of fostering a vibrant scientific landscape. So indeed, there is a significant hope and potential for the advancement of science in Africa, of course. Over the past years, there has been a growing recognition of the importance of scientific research and innovation in fostering sustainable development and addressing global challenges. So I can sit here several reasons why there is optimism for science in Africa. So in Africa, as you know, we have ITIMBA Labs, a multidisciplinary research facility located in South Africa. And it's worth noting that ITIMBA Labs plays a significant role in advancing science research, not only in South Africa, but also in the broader international scientific community. Also, Africa has been increasingly engaging in international collaborations in various scientific fields. We have CERN collaborations, African Space Research Program, African VLPI network, and the most recently, Africa had joined the Electron-Ion Collider effort, EIC effort, where they are Algeria, Egypt, Morocco, Senegal, South Africa, Tunisia, and Zambia. So this participation here aligns with the broader trend of African countries increasing engaging in international scientific collaboration, contributing to the global scientific landscape, and of course, promoting the development of scientific expertise within our continent. So this slide here shows more on scientific infrastructure initiatives in Africa, including, of course, African Light Source, X-Tech Lab, Square Kilometer Array SKA, and Masin Moroccan Agency for Solar Energy. All right, so yeah, this is there are not enough scientists in Africa, unfortunately. So Africa is home to 50% of the world's populations based on UNESCO Science Report 2017, but it produces just only 2% of the world's research outcome. Only 1% of global investment in R&D is spent in Africa, and to achieve the world average for the number of researchers per capita, Africa needs another million new PhD. So the situation is getting worse because there is like a lack of opportunities. Africa lost roughly 20,000 professionals to high-income countries every year. So according to the World Economic Forum Annual Meeting 2020, 2 in every 5 children will be born in Africa by 2050. So the big question here is what needs to be done to give science and technology their due weight in the development processes. So as you know, the African Union and African Academy of Science have developed top-down strategies for the continent. But of course, this is not enough. What we need now is seeing how other regions of the world are organizing themselves to define their strategies. We African physicists in Africa and from the diaspora should feel complete to come together with international partners and policymakers to define the education and physics priorities that can be most impactful for our Africa. Now, I would like to introduce you to the AfPS project. The African Strategy for Fundamental and Applied Physics, AfPS, aims to define the education and physics priorities that can be most impactful for Africa. So this project has a vision that Africa is an ideal location for global research infrastructures. So in this project, we are going to develop a strategy to increase African education and research capabilities. And of course, we are going to engage African scientists and also international community from all countries in this strategy development to improve collaborations. So the process of AfPS will last few years to end up realizing the final report, and this report will suggest the direction which actionable items for the next decade. And of course, it will repeat it periodically, let's say every 7 to 10 years for the following decades, with, of course, a review of the impact from the previous strategies, like what actions were taken, which were not taken, how do we revise the strategy, given current information, and so forth. So here we have AfPS organizations. We can see the committees, the working groups, and the forums. So the steering committee the steering committee will be the go-between. So this committee is the one driving the efforts of communicating with International Advisory Committee and also communicating with the working groups, making sure that everything is evolving according to plan and will be responsible for drafting the final report. We have also the International Advisory Committee. This committee will be reviewing the progress, making sure that we are on track, and will be advising us on the scope, and also will be engaging with international committees and policymakers. And also at the end, they will review the final reports. And then, of course, we can find the observes committee, the ethics committee, the physics working groups, and the physics sub-working groups and liaison. And also, we find here the engagement forums, community engagement, physics education, women in physics forum, and also young physicists forum. And each group has 3 to 4 co-conveners to go on with this strategy process. All right, so since the creation of this project, ASFA project, we received the support and the endorsement from many organizations and many institutions, among of them in Africa. All of these are here. We have the African Physical Society, we have African Academy of Science, African Union, and many institutions in South Africa and North Africa. Also, we have support from many kinds of societies and many other organizations like CERN, ICTP, and even UNESCO. So ASFAB, so in this slide here, we can see the founder of this project from Pan-African and African diaspora. And also here you can see our International Advisory Committee. So ASFAB has 16 physics working groups on physics area relevant for strategy development in Africa. We have accelerator physics group, astrophysics and cosmology, atomic and molecular physics, and so on. And also we have 6 societal engagement groups necessary for human capacity development in Africa. We have a community engagement, observes committee, ethics committee, physics education, women in physics forum, and young physicist forum. All right, so concerning the ASFAB timeline, there were a lot of preparation made from mid-20 to mid-2019. So in June 2020, the steering committee launched the effort with a funding document, the formation of an international advisory committee, and the formation of working physics groups and areas of engagement. And the official launch of the project was during the online workshop organized jointly by the African Physical Society and the African Light Source on November 18, 2020. We had our successful town hall in July, and I believe some of you were there. And also we had a Pan-African Physics Roadmap community discussion with the African School of Physics alumni in on October 19, 2021. And we are now in our stage 4. So all the white papers will be finalizing by that time to help us have a moderated shape of our reports. And by the next year, we hope to celebrate our ASFAB symposium and community feedback. And and also to realize the final report will be endorsed by our International Advisory Committee. And of course, this report will be submitted to the African Physical Society, African Academy of Sciences, and other stakeholders in or outside Africa. So this slide here shows some of the mission of ASFAB working groups and the ways to contribute in this great project, either by submitting the letter of interest and participating in with paper studying groups, working groups, and also sub-working groups. So our final report is now in progress. So a draft of the final report is in preparation, and all the working groups are expected to contribute to it. And at the conclusion of the draft report, we will organize a symposium to present the report to our international community and integrate further feedback from the symposium to prepare the ultimate final report. And the date and the host country venue of our symposium still to be decided. So I will invite Dr. KTV Asamagan to lead the second part of this presentation. It will be about a discussion on the community buy-in and financial resources.
Thank you, Munia. You have described this so eloquently as to leave me scarcely with anything else to add. My name is KTV Asamagan. I am a research scientist at Brookhaven National Laboratory in New York. I do research in experimental physics, AfLS, high energy physics. So what I would like to do here is more having a discussion. You have heard from Munia the evolution of the African strategy from grassroots physicists' point of view, all the way to the final report, which we are working on right now. And one question that we have been hearing, or we have been dealing with, even before the report is actually prepared, is about implementation. And we know that the top-down strategies that were made by the African Union or the African Academy of Sciences, all of these large bodies on the continent, they have had problem with implementation, because that requires money, that requires politics, that requires priority alignments of different countries or differences in priorities and so forth. So then what we are doing now, when we get to a place where we have a report, we will also eventually face the same issue. I don't have an answer to it. That's why we put it as a discussion. You may have your views. We would like to hear about that, but we should start that discussion now before we even finish the report, so that when we get to that stage, we have implementation pathways, so that this report does not sit and collect dust. So implementation will, in my view, require really two things: community buy-in, which essentially means, when that report is out, does the international community believes that we and the people who have been involved in preparing that report have the authority, the capacity to produce something like that, which they need to listen to or they need to look at. Yeah. So that is a community buy-in. And then if they do believe that, yes, this community, international community, did have the capacity, there was a lot of grassroots involvement. These are the community of physicists in Africa and internationally who came together. So these are physicists, scientists. So therefore, the report on the scientific point of view is authoritative, is authentic, it's done by people who know what they are doing. Yeah, therefore, politicians, policymakers should listen to it. Now, if they do get to that stage, well, listening to that report and trying to use the report or part of it require resources, financial resources. Where do the resources come from? Yeah. So that's the other questions. So I would like to just leave those points there, and maybe there are other there are other points in terms of successful implementation that you may have or you may suggest, because as we finalize this report, we need to also talk about the outlook. Where do we go from the reports, which is really the implementation? How do we start that process of implementation? Yeah? Who do we talk to, and so forth? And how does that get presented to the people with power or the people with the resources to make sure that the implementation phase actually becomes successful? So I would like to stop there and hear from the audience if they have any suggestions or any experiences themselves in terms of what we should be thinking about when it comes to the implementation phase. And I would like to take the liberty to jot down your ideas, and I'm doing that. Like I said, I don't have the answers, and we would like to be able to get your input as we finalize the report and say that this is what the community is saying about how we can be successful at the implementation phase. So if you have any ideas, any comments, any suggestions about implementation.
I can see Simon raising his hand.
Okay. Simon, just hold on a second, okay? Please go ahead.
Thank you, Munia and Kitevi, for your contribution and for being part of the conference. I think from my point of view, the AfPS process could be seen in the first place as a little disappointing in terms of the community response. It is community driven, but I had higher hopes in the beginning there would be more community involvement, that we would have had a bigger geographic footprint and generated more of a conversation. So the only thing I can come up with there is that it's a process, and we have to be satisfied that there's probably some apathy in Africa in the sense that we are not used to our policymakers listening to us.
Simon,
Simon, yeah.
Okay.
Yeah.
Before you continue on that point, let me just tell you that, Amunia, could you go to the next page? So our next point of discussion is really about that issue of how do we improve upon the strategy that we have now.
Okay, then let me go back to the previous one.
Yeah, if you can talk to, if you can talk about.
I didn't know you had the other one. Yeah.
Okay.
So what I thought here, specifically here, is there should be a process to form a implementation committee, which maybe from the community-driven side, it only obviously it can't implement, but it can maybe be like an advocacy group for that to happen, just as a placeholder before the next strategy, that we do have some mandated body to arise out of the current process, which can call itself, the implementation committee, and is really just to report on that, assess it from time to time, and be an advocacy group for that, and to have formal standing that it still arises from the community-driven process, and to try and build some continuity until the next process. So I'd really like us to form such an implementation committee.
Thank you, Simon.
KTV, hi, can I add something? Hi.
Yes, please. Yeah, please. Let's make it short, okay, so that other people can also talk. Go ahead, Farida.
Yes. Hi, everybody. So just to, the process of AfPS as FAP it is, I mean, we are in the fourth years. So what we have learned, what we have learned, there is a really a big issue with community to be involved. So arising now, the point that we need to discuss the implementation, it is absolutely our big objective from the beginning. The strategy is a process in which the community, African scientific community, must be contributed to catalyze any issues, any perspective, anything related to it. And then when the final report was at the beginning, then we discuss with the policymaker how we can really perform an effective implementation. So in the first step, which is the involvement with the community, based on our experience so far, ASFAP is a great project. We need it for Africa. It is absolutely no doubt about that. But what we have learned that we need some kind of education, to have education in the sense awareness that the communities have to be involved, and then the implementation. So if we manage to have this final report, we need, when we talk to policymakers, the language should be different. We will not discuss that the community, we cannot arrange with the community. The report should have some conclusion in which talk to the community itself, to have the continuity for this strategy, and focus on the main issue that we will be sure that get implemented at the policymaker level. Thank you, KTV.
Thank you, Farida. Anybody else would like to input comments on this particular implement? So please, I would like to say, restrict your comments to the issue here, implementation, please.
Yes, I think that from the beginning, the African strategy was supposed to write a report to be given to African Physical Society, and now I understand also to African Academy of Science. So, as far as the implementation is concerned, it is up to the policymaker. Maybe now we have to find maybe another strategy how to make the policymaker make the implementation, because there is a working group, and all the working group have to write the report, and there will be a general report to be given to African Physical Society and listening to you, and also to African Academy of Science. And after now, we have to how to make the policy make the implementation. We as a science community, we cannot make this implementation. How we are going to do it? This is my question. Okay, I finished.
All right. Professor Wage, thank you very much for that input. I think on your point is well taken. As a science community, our first scope is really to deliver the reports based on scientific engagement within our community and internationally. But I hear from Professor Simon Cornell that we need to go a bit further than that as scientists, and to also, dive into how to convince policymakers to do that implementation through a new advocacy group that he is suggesting to take. So having to take on more political role in knowing how to talk to policymakers, it becomes increasingly important for us scientists to do. I think that's what I have gathered so far. If that's not correct, you can, either you or Simon or anybody else can redirect. One more input on this point before I move on to the next one. Anybody else has anything they would like to say here on implementation on the issue of implementation? All right, so Munia, let's go to the next page. Now, we have touched upon this a little bit on the point of view of strategies. In other parts of the world, they repeat it periodically grassroots strategy, okay? Not countries' own strategy, could be 5 years and so forth. Grassroots strategies, European strategies, the US snow mass and so forth, those gets repeated every 7 to 10 years. And even if the report that they produce, the action item they came up with in the previous strategy were not all implemented, they are not discouraged by that. They redo it, and like Munia said, they see what has been implemented, what was not implemented, and how to adapt new strategy development to current scientific and societal realities. So then it becomes a culture. It happens anyways. Yeah. So how do we get that process to happen periodically anyways in Africa driven at the grassroots level by African physicists who will not be discouraged that part of the reports or recommendation in the previous strategy were not implemented. Nevertheless, they come together anyway and they review it, they adapt it. First, because it brings the community together. We begin to know our friends from the light sources, material physics, and they begin to know us in particle physics. The community is working together. That's actually noble, and we need that. The strategy can achieve that. Yeah. So one of the things which Professor Farida has touched upon, and I think Professor Simon also mentioned, was the fact that we had a problem driving the grassroots physicists in this strategy that we have developed. Participation was low. Yeah. How do we make it better next time? Yeah. How do we bring in more of the physicists in Africa and internationally to come together next time and say that I want to participate in this work because it's this important for the continent. Yeah, I would like to leave it there. But of course, the issue of low participation touch upon issue of implementation because it touch upon issue of legitimacy.
Exactly.
Yeah. If
I want to say something.
It was not developed by a lot of people, then it does not, it's not, in point of view of implementation, it doesn't really hold, right? So how do we make sure that when this thing is repeated later on, we have more participation from the continent?
Yeah. Can I say something?
Please.
I completely agree that the strategy must be repeated periodically. As for that, I agree completely. And coming back to the implementation, maybe we have to learn implementation in the other part of the world, in Latin America, in Europe, how they did it. This could be maybe an example for us. It's all.
Thank you, Professor Wage. Somebody else want to say something? I noted that down.
There's Galileo.
Yeah, yes, Simon, I would like to make a comment about the method of politicians. Listen, the method of politicians is something which is always discussed and is a problem. However, I think that to think about politicians as if they were a monolithic body is a mistake. I think what one should find is to identify a few politicians who understand this thought and use them in order to convince others. But if one thinks about politicians in general, you will always face the problem that you have other problems, that there are things which are more important, more urgent, and so on. One must identify in some way some people who understand this, and usually they are, and then try through them to convince the politicians. And for this, and there's another thing which is very important, which unfortunately, I'm not saying something which I'm saying in Latin America it's worse. We have the same problem in Latin America. But for example, one thing I think is very important is that we should everywhere try to form a number of the people. Sorry, of people, for example, who are able to write, journalists who are able to write about science. I mean, politicians can be convinced if the civil society supports it. The two things go together. This is not a big discovery I'm making, but is the comment I would like to make.
Very good. Thank you very much. It's very well taken. Anybody else want to add something?
I think Maureen want to say something.
Hello, can you guys hear me?
Yes.
The bit about politicians, I don't necessarily think they're as big of an obstacle, as long as there's production in the light source. So like it depends on the country. A lot of times, different countries in Africa have different sorts of policies, and for the most part, I think it reflects well on them if they're scientific discovery of some sort. That's all I want to say.
Great, thank you. Gihan.
Hello, Kevin. Thank you for this nice presentation, informative also, together with Monia. I just shared the link to the survey that we launched through the ASFAP Light Sources Working Group. I just invite the attendees also to help us with this and to fill it out together with the link to the survey of the African light source. Thank you.
Thank you, Gihan. Any last comments on both issue of implementation and issue of grassroots participation and periodic development of strategies in Africa? Okay, so on that note, I would like to thank all of you. If later on you have any additional comments, by all means, send it to us. You will see the email of the steering committee is on this slide on the first page. There's our email address there. By all means, send us further input on any of the points that have been presented. I will let Monia take you through the conclusion.
I guess since you are running out of our time slot, I just want to thank the African Light Source for this opportunity to give a talk and also for this wonderful event. And so, yeah, thanks a lot.
Thank you very much. Really appreciate your talk, Professor Lasiri. Very nice. And if there's any other questions or anything, you can drop the email or whatever we try to get you to. If we look at the program, we discover that at least we're supposed to be on a break now. It must be 15 minutes break, but due to the time, that means we are going to have just 10 minutes break. I'll continue our next session. Okay, so for 10 minutes break. Simon? Lawrence, are you okay with that? Yeah, because we can't.
Yep, that's fine.
Okay, thank you. See you soon.
All right, yes.
Lawrence.
Yes.
I just want to remind that this is a joint meeting. African Light and African Physical Society, isn't it?
Yes.
Okay. So I want people to know that.
Yes.
Hi, Lawrence. I'm here, getting ready in 10 minutes.
Sure, sure.
All right. That's again.
So, right. I'm looking up the word barnacle.
Yeah.
You know, I was in the Navy. We used to use the word barnacle all the time. I never really thought like what it actually, what's the scientific definition?
Veronica?
Barnacle. Like the barnacles on the bottom of a ship.
Yeah, barnacle. Yeah, yeah.
It's usually someone's job to go down to the bottom of the ship and scrape off the barnacles.
Yeah, in my math class at U of M,
Not one of the best jobs the Navy has to offer.
Nkem, are you in South Africa?
No, actually, I left Cape Town on Thursday. I'm now in London.
Okay.
I'm at a meeting here in London. I just took off a few minutes to go to take care of this, and I'll go back to Nairobi tomorrow.
Okay.
But things look good. Things look good. I'll update a little bit later. But you're meeting with Ken. Please meet with him. It will be good to be very low tempered, just for what we can harmonize. I think there's a good prospects that without trying to protect tough or chest up on who is who and point fingers. There's plenty of stuff in the spirit of the email that you sent us that the AAS work can seek for resources that can be very good for the AfLS.
Yeah, we look forward.
That I think I can do.
Thanks, Nkem. Should be good.
I think I can do. We just need an atmosphere that's less contentious and very, very and very mutualizing.
But when you come to our country, please stop by.
Whenever I'm in Johannesburg, you know, I can go without saying hello to you. Tell me, Science Forum South Africa, SFSA, next month in 2 weeks. Is that an annual thing or biannual or every 2 years?
No, it's annual. And it should maybe be not Science Forum South Africa, but Africa, because there's a huge African participation.
And that's what I'm planning for next year. That's why I'm asking this question.
Yeah.
I'm going to get down to Tuat and Finjura later this year. The Academy President, Liz Korn, and the other, Liz Corsten, and the others I'll let them discuss that with DSR.
Yeah.
Because last year, they actually did it concurrently with the World Science Forum in Cape Town. They didn't do something separate. They did it together.
Yeah.
So the seed they've planted down there can go to the continent now.
Yeah.
That's how you put it so that
would be better.
That's how you put it so that they can feel that they're credited for what they did. So that it's not a conflict between what they do and someone else. You just start from where they are and say, let's grow it to the continent.
Exactly. You can maybe bring it to Kenya.
That's my thinking.
I think there was a minister a few years ago that suggested that, you know, there's Science Forum South Africa. The meeting should be in Kenya, right?
The thing is, the minister...
But you know, again, what he has to do is make a meeting in Kenya. I mean...
Exactly.
You got to make your breaks in this world. So South Africa puts on that meeting. They spend a lot of money on it.
It's like what you were saying, Laura. It's like what you were saying, Lawrence, earlier on the previous talk. Ministers and political folks shouldn't say, I wish it is done this way. I would like to see it this way. You have to do it. You want who to do it? You're the one with the purse strings and the policy strings. So when our leaders just say that it would be good to do this and acting like they are outside agents and recommending someone to do it, problematic. That minister should have said, let's take it, give it to me in my country. I'll take it over. We'll put the budget.
Yeah.
Bring it to
a few years ago, I guess, when he was deputy president, Cyril Ramaphosa spoke at Science Forum South Africa. And actually, the speech is online. It was actually very interesting. He covered a lot of bases. But he said, well, it was a funny time in South Africa when he was vying to move from deputy president to president. He said he had a part 2 of his speech that he was going to come back and give. So it'll be interesting to see if they hold him to that now that he's the president. Will he give part 2 of his talk? But the point is, I mean, I know the ministry put in a lot of work to get people there, including their own deputy president, which, you know, he was there and it was a total madhouse with all the other people that, you know, is people that come along with when you have the major politician. It was, you know, standing room only in the auditorium. Actually, some people even had to stand outside. So you have to make a lot of things happen.
And the logistics, deploying the security system, visa and foreign policy, the whole government has to be deployed for something like that.
Yeah, yeah, because yeah, it was not. You know, Barack Obama spoke at a AAAS meeting, whatever year ago that was, and the logistics was just out of this world. And in the end, I felt like you could have just sent a recording and could have saved myself a huge headache. I have this other Barack Obama story. There's a neighborhood bookstore, an independent bookstore that's on the block where I live, and I guess for Christmas shopping one year, President Obama decided to shop at that store, and let's just say our street is not set up for that. The number of vehicles and stuff that came along with it. Of course, it was unannounced, and I was like, you have got to go.
No, I'm going to share with you guys. This is recorded, right? So I should watch my words here.
Yeah.
Lawrence, I think you should kick us off. I mean, sorry, Nkem.
Okay, yeah.
Isn't somebody?
Time is running.
Is it time? Yeah. Okay.
Is everybody here?
Yes. You can start.
Yeah, I think a lot of people are here.
Should I share my screen? Can you see my screen?
Yes.
Yes. Now it's full screen.
Now it's full screen. Should I? Let me know when I should start, Lawrence.
Yeah, go ahead and start.
All right. So my name is Nkem Kumba. And for at least for our audience here, I do serve as the current chair for strategy and policy with the AfLS. That's hosting this conference. And I followed the previous few talks, and the issue of strategy and moving forward came up substantively, which I would touch on a few. And I also recently moved to Nairobi to serve as the head of STI policy systems and governance and partnerships for the African Academy of Science, which is a new position. Many of the challenges that have been remarked about the academy are very valid. The academy has its ways over the last few years it was founded, but it's policy, advisory functions, which are about the core functions, advise governments and the overall international community and African scientists on the matters pertaining to science and African development. So my role there is to help lead that function for the academy, and I'll share a few more on that. Now, the comments that the previous talks have touched on much of what I would say is a common space. So there are many cross-cutting themes. It's the same Africa we're talking about, the same demographics, the same everything. So much of this would be repetitive. I would save that by making maybe my remarks a little shorter. It's not a technical talk, and I was advised to give a Pan-African administrative perspective, policy perspective, let me say that way, as I see them. I'm not a minister, even though they say a ministerial perspective, but it's a view that for some of us who've worked with the policy establishment for a long time, we've come to discern from them. So what's this here? Let me get my thing here. So this is the general perspective that one is functioning under. The Pan-Africanism, talk about a Pan-African perspective, it's a long-standing concept that many of us know. I don't know how actively we are in governance issues and African history and African development, post-colonial, but Pan-Africanism has been the main organizing principle on which Africans have felt that they cannot work by themselves. No Africa is viable alone. Some of them are very small states, barely functional, and I say that in a very positive way. And some are big. South Africa is big, Kenya, Ghana, Nigeria, Senegal, but some countries are not viable. So our famous leader Nkrumah would say that, one country alone cannot do it. You need the independence of one country is not sufficient, and the independence of Africa as a whole is still insufficient as long as one country is still under colonial rules or domination. So Pan-Africanism has been the overriding principle that Africa must work as a team, as one continent, possibly one country. But nevertheless, the only way forward for Africa emerging out of the colonial and slavery period is to organize itself into a team, otherwise it will pick apart. But in that post-colonial period, Africa mostly focused on self-affirmation. Previous 400 years of slavery and colonialism had questioned Africa's personality, humanhood. In the US, they would say Africa is 3/5 of a human being. And we have books on history and literature that portray Africa as animals, as subhuman in so many ways. So Africa's post-independence priorities set by their leaders in the 60s was to reaffirm their humanhood, self-affirmation. That was big. And so the humanities were the big part of our higher education systems. Humanities. And we've had Nobel laureates after that. The Soyinkas, people like Seda Senghor were big. You have negritude. You have African literature. It's very strong. So humanities was a key feature, a primary focus of post-colonial African higher education and policy priorities to reaffirm themselves as full humans on the planet after being questioned for centuries. The other aspect was self-governance. They were just taken over from the colonial folks who had ruled the continent, from cradle to grave. So how would they govern their countries? They were colonial governors and middle management. So Africans had to take over. My home country, Cameroon, for example, at independence had only 3% literacy rate. That is 3% could read and write. So understanding the apparatus of government, the machinations of government was not very clear. So post-colonial Africa, about 1960 to about 1970-80, the focus was on self-affirmation and self-governance. You see in higher education reflected in that. Humanities and social sciences, economists in every sphere, literature, culture, history, philosophy on every sphere. Even though some called for science to be a key part of the tool of education for the tools that Africa would need, people in Nkrumah and many others already knew that science is the only tool that Africa can use to advance itself, but it wasn't overly emphasized. And so these two are emphasized beyond science. And you couple that with external pressure. Just around in the mid-70s, the World Bank put up a certain study that said investment in primary education yielded higher returns than investment in university and postgraduate education. So as the key underwriter of African economies, they insisted as a condition for loaning African governments money to run their countries, that the money should go back into primary, secondary education and not higher education. And so many African governments did not put money in higher education. And that's part of why we see this low STEM productivity. Around independence, there were key universities on the continent. What I would say, our equivalents of the Harvards and the Oxfords. You had Makerere as the Eastern African Regional University. You have Ibadan. You have Furabe. You have Yaoundé. Many of the independence leaders were trained there. Top scholars that left went abroad and created records. But this policy that held African leaders' hands from investing in higher education decimated these universities. Makerere is not what it used to be, neither is Ibadan, neither are all these regional universities. They've become like shares. No investment in that. So sometimes when we say Africans didn't invest in higher education, we didn't do this, where's our money? That's part of the explanation. Those who paid the piper, the World Bank and the big institutions, insisted to African countries, higher return comes from primary education, bring every girl, bring every villager, bring every handicap, expand the pool of primary education, but in higher education, that was a no-go zone. That's a key explanation that since the 70s and 80s, Africa has not been able to repivot its investment into higher education to give us the kind of sciences that we are aspiring to have through something like the light source. So when we put in perspective, the dependence on the outside funding has really been a big problem. And another effect of that is that conditionality on funding for African economies, also on the right of African economies, it structured African budgets, even parliamentary tax allocation to the different functions along those lines. Up to now, governments have a hard time reorganizing and pivoting their structural finances. Ministry of Finance, of Economy, this issue of insisting of focusing on the exporting raw materials, it all came from that conditionalities, where the dominant powers say this is what you should do. And many African leaders do not have latitude to go beyond that. Some of the coup d'etats and independence movements and counter-independence movements, revolution, counter-revolution, they came from that dynamic of those who said we have to do science, we have to develop ourselves, master our own environment, be master of our own planet, of our own environment, versus those who wanted to go with the international community. So that explains between about 1960 and 1990, all the, well, we'll call it coup d'etat, but for them, they were calling it revolution and counter-revolution in the sense of Marxist pro-East or pro-West and similar. So it had it resulted in Africa having very low STEM activity and productivity. This map here, I think many have said this already, so I don't need to repeat it. But at the bottom left, at the bottom right there, you will see that little string coming down under patent. It's just kind of, an extreme clarification of what we mean by completely low productivity, almost insignificant, almost doesn't exist. And that explains Africa's position on the globe, that while the rest of the world is advancing scientifically, we're lagging behind. But African governments themselves have been trying their share, so it's not like they've been dormant. In 2014, the African Union carried out a survey to develop. 2014 happened to mark about 2013 or so. The AU is a successor of the OAU, Organization of African Universities, of African Union. That was founded in 1963. So in 2013, that marked its 50th anniversary. And around that 50th anniversary, the African Union considered Africa's next 50 years, which ends in 2063. And so they had their agenda. That means, that was the background to that policy document. And on that roadmap towards 2063, their first action item that they all understood very well was science and technology. So they came up with a strategy called TISA 2024. And that was supposed to guide them on how to make science and technology the upfront major engagement on Africa's road for the next 50 years. So that was what that policy strategy was supposed to be. Right, 2024 expires next year, 1 year from now. And right now, I was actually just in Johannesburg last week. We're discussing how to develop TISA 2034. Now, as a policy document, it has its strengths and weaknesses. The previous speaker talked about implementation. What has TISA done to Africa? What could it have done in the first place? I mentioned earlier that the African budgetary, government, financial structures are still very much pivoted away from high-end science and higher education. So TISA, even though it's a continental body and many African governments know about it, the allocation of the resources and the implementation was still a challenge. I'll get back to that. Under President Thabo Mbeki, who came as a very visionary Renaissance man for Africa in Africa, proposed NEPAD. The African Union had been working just as a consortium of presidents who meet annually to consider whatever is of value to them. There was really no development agency in Africa. Africa had all these relations with Europe, with America, with the outside world, but there was no structure to say, let's do development on behalf of Africa. There was none until Thabo Mbeki came in. And there would be him and Olusegun Obasanjo of Nigeria and Abdoulaye Wade of Senegal came up with NEPAD. NEPAD then became the agency through which continentally Africa would implement its development plan, whatever the development is, science, extractive industries, defense and security industry. So all of that was under NEPAD. Now, one of NEPAD's earlier activities, again, was to look at science as the first item. So they developed their own science and technology action plan to look at all the African landscape and consider what is happening on the continent of science, consolidate them into its own umbrella and say, we are the AU Development Agency and implement it. So they have the African Development Bank as Africa's premier continental financier, owned by Africa. Well, not owned by Africa 100%, but Africa focused. The World Bank and the others have, they're globally focused, but this is Africa's own bank. Yeah, incidentally, the African Development Bank was actually founded and mostly sponsored by Nigeria. We should know that it's the Nigerian leadership that they put that together and infused the initial funds to make it. So they also have focus on higher education. They have their own plan for that. If you post-Cold War, when Eastern Europe break loose, many African countries who were caught up between the East and West started revising their own planning, their own agendas. And many came up with what they call development agendas, to become emerging nations. 20, 30, 40 years, I'm sure for those of us here who are familiar with African countries or where we're there, we know of some country having Agenda 2030, Agenda 2040, all the various agendas. In those vision plans, almost every African country puts science at the forefront. Whether they do it well or not is another issue. But they put science at the forefront, human capital in STEM fields. So I bring this up just to clarify that the question of science is not absent on Africa's ministerial or governmental policies. It has always been a key factor, an upfront factor that they recognize very well. The challenge has been how to implement it, how to go from idea, from vision, from intent to actually actualizing those the policy on paper. Now, the World Bank that actually told African countries in the 70s not to support higher education, and if need be, after this, I can share that article. I can share that article that indicated return on investment. The World Bank, about 10 years ago, reversed course. There's a Senegalese economist, Makhtar Diop, who became the vice president at the World Bank for Africa. And he reversed course and said, well, Africa has put money on science. But by the way, it didn't come from only that. A few years prior to that, Paul Wolferson, when Mandela came out of prison, they visited Paul Wolferson. Paul Wolferson said, "Mr. Mandela, what can I do for you? What would be the most important thing to do for Africa?" He said, "Support science and technology." And so the World Bank itself realized that many of the global questions that were being addressed by the bank, climate change was already one of them at that time, among others, agriculture, science and technology was a tool that they needed. So the World Bank was already putting money to support science and technology, not because they wanted to support African development, but because they needed those human capital to address what the World Bank wanted to do. So Marka Diop recently established a Center of Excellence now to grow that World Bank science activity into an African activity, give some appropriation to Africa. The structure of those centers still followed the certain World Bank model. The funding model were loans to African countries. And the technical implementation, the technical leadership came from the World Bank, not from African countries. But nevertheless, it supported Africa. There are about 44 of them in West Africa and Central in West Africa. Our colleagues here in Ghana, Nigeria, and Senegal, they will know about that. East and Southern Africa has some as well. So all of this was to just clarify that our African leadership have been doing their own best to put science at the forefront. Amidst all the different global pressures and domestic conflicts and other priorities on their table, science has not been absent. So when we have these conversations, we should keep it within the context that we are trying to simply follow, or at our own level of being practitioners as physicists and engineers, follow or complement or implement what our African leaders themselves have been thinking. So here are some of the institutes that exist across the continent. The Nelson Mandela Institutes, there are 3 of them, one in Nigeria, one in Burkina Faso, one in Tanzania. Those institutes were created as a response to what Mandela told Paul Wolferson at the World Bank: create centers of excellence, of research centers. NEPAD has centers, the African Union has centers, where we've mentioned the SKA is the most ambitious and more well-known on the continent. So Africa has been shifting itself towards science. So we are really not doing something that is new or out of place in terms of the political landscape. But now, in the last few years, actually just about 3 years ago, the free trade area came in just 2018-19. You know, the new crop of African leaders, post beyond those who gave us independence in the 60s, a new crop came in and had to change the discussion. Post-colonial was political liberation. We don't want to be dominated by the West. We don't want to be colonists anymore. But now that wasn't sufficient. We need economic empowerment. We need to master our environment. As Nkrumah would say, we need to be able to manage and mismanage ourselves without anybody interfering with us. We need our own manhood and womanhood. So that shift from political liberation towards economic empowerment led them to create the Continental Free Trade Area in an effort to create one market. And the free trade area is also a way to integrate the continents. Since Pan-Africanism did not quite work, Pan-Africanism was political, and countries tended to emphasize their independence as nations more than the collaborative Pan-African mantra that was advocated. So it became difficult to even talk of one Africa. Even West Africa didn't make sense the way they operated. East Africa, all the regions, you're talking regional activity, but operating independently, things solo. So the African Free Trade Area is a detour, it's a contour to try to implement Pan-Africanism without political confrontation, political aspect. Do it through trade, integrate humans, university, mobility of goods and services and human beings. Just integrate the continent and the rest will follow. Almost like Europe, not the same spirit, but almost like Europe. But that means that the continent with an economy of about $3 trillion at the time of the free trade area signing would grow by about 3 times within 10 years. Why? Because Africa would trade with itself, not colonial structures. The Anglophonies in Africa trade more with England. The Francophonies more with France. The Lusophonies more with Portugal. Africa as a whole more with Europe. Now more with China than with itself. You've heard comments to go between Cameroon and Nigeria, you have to change your CFA or even the West African currency to go from a French-speaking West African country to Nigeria or Ghana, you have to switch out, you have to exchange to dollars and then get back to your neighbor's currency. Too many bottlenecks. So when those are taken off and goods in one country can easily go to a neighboring country, the intra-Africa trade explodes. The money circulates within the continent, and that's how the economy goes from 3 to 7 or trillion or so fast. For that free trade area to work, Africa recognizes again our leaders, our presidents, our ministers. These policies are developed by our ministers, most of our ministers, our ministries, let me say it that way, under their aegis. So integration means infrastructure. What's infrastructure? Roads, like the arteries of the economy. IT infrastructure, resource development. What does it mean to beneficiate? What does it mean to add value to process our raw materials before export, be it agriculture or oil and gas and minerals? It means manpower. What does it mean to do commerce? Tools of modern commerce are technological, fintech, cybersecurity. Most African countries cannot do good e-commerce because of the IT infrastructure. And IT is not just the computer that you buy. It's cybersecurity to defend and protect the banks that were involved in it, the defense systems, on all the ecosystems around e-commerce, industrial manufacturing. So all these things say space and security and defense, food, water, energy. So all these things are what Africa is telling itself. We have to emphasize on this in order to integrate as a free trade area and share this good among ourselves. Where one country is stronger, let them aggregate their resources to help the weaker one. That's the spirit of the free trade area. But all these different things that are on the table now on the continent, the leadership recognize that they're all contingent upon advanced scientific workforce. You don't do them on paper by policy. You do them by actually developing the scientific manpower for that. And this is not just skills at the vocational level only. These are frontier science. If Africa has to have a place on the globe and have some respectability, it has to have the scientific know-how to compete with the advanced world. China was where 30 years ago. Where was Korea, the Asian tigers? Can Africa think that? There have been so many, I've come across so many African ministerial trips, travels to Asia to quote unquote learn the Asian miracle model and see how to replicate in Africa. How many go to Europe and to Africa, to America for that? Well, success or not is another issue, but the effort is made to say we have to develop the relevant manpower, scientific manpower, to find our place on the globe. This issue, friends, is not lost on our leadership. Whether we are frustrated with them, they do well or not, implementation, as I heard earlier, is an issue, but it's always been there. Now, if you focus this, if you combine this imperative to create a free trade market, a one African market, with Africa's own demographics that was mentioned earlier, that just by the youth bulge that's been indicated, there are implications, big time implications, that between 2015 and 2035, 20 years old, that's about up to 10 years from now, 3/4 of expected youth population, college age, will be in Africa. 3/4 of that will be in Africa. The top 10, actually, of the top 10 will be in Africa. Angola, the DRC, Ethiopia, Kenya, Nigeria. This concentration of big youthful population is a demand on higher education. It's a youth bulge that, if not well tooled in the skills that will give them a space to be global players and competitors, in their frustration, there might be a liability to the continent and the globe as opposed to an asset for global development to contribute to global well-being. So the demographic bulge that we're quoting all the time in many media creates huge pressure on Africans to see that even those who are having difficulty creating short-term solutions can at least put in, because it's politically sometimes not expedient, but can at least put together policies that would provide space for these young people coming up on the continent to be contributors to a future that is even more technological than it is today. We talk about artificial intelligence, fourth industrial revolution. In the next 10 years, when these young folks come up, it will be even more than that. What does it mean? Where are the skills, the tools to educate them? So our university systems are getting overcrowded. They're getting pushed out, pushed. As a matter of fact, in some countries in the Eastern Africa and Southern Africa, I know in Nigeria also, new universities, as simply they call them, STEM universities. You know, they are not into philosophy and humanities and social sciences as once post-independence. They are mostly focused on they are mostly, yes. Am I going too far? Am I taking too long? Okay.
Yeah, why don't you kind of finish up? Yeah.
All right. So, the need for STEM is across the board. Let me just mention this last item that came out of a continental meeting, the first continental meeting on science and on higher education. The very first one, a summit, was in 2015. That's post-independence. After about 50 years of independence, that's when Africa arrived at having a summit to review with itself its higher education and how to revitalize it. One of the key features that came out of it was the need for a central synchrotron, a central large-scale facility to bring advanced science practice on the continent. As been mentioned by our leaders here, Simon and the whole team and much here, to cut the hemorrhage of brain drain and empower Africa. So the issue of the light source as an infrastructure is very well known, is well acknowledged that many countries cannot even discuss light source because they don't have the capacity or the competency, and let's be very clear on that, to handle this topic or to handle this equipment. It's high tech, you know, it's high scale, but they do realize that in the absence of being able to handle it by one country, there is need for a consortium of countries to come together and do one. Just like at the level of development, you have East Africa, West Africa, ECOWAS, they do regional. So a regional approach to advanced science is what, just like, again, many research centers are regional. There's hardly anything that's national. Many are very regional. So the idea of a light source as a central research point for advanced science, at least the initial one, who knows, there might be 2 or 3, 50, 100 years, who knows, but at the first take, start with one. So that was already been mentioned. And stay out of that summit in 2015, the African Union, recognizing this issue of science and technology, further beyond their policy statements, established a committee of 10 heads of states, said at the level of the top policy making on the continent, these 10 heads of states should lead a science agenda for the continent. They should champion science beyond words and declarations, and make sure that what is being decided at the African Union manifests itself on the continent. Now, Africa being political, the C10 hasn't been very effective. I know they had their first meeting in 2018, just 2 years after being established. COVID came and perturbated many things. I know they haven't come back to it, but it's hosted at the AU's secretariat. So these are Africa's own political thoughts and engagements that clarify to all of us doing this work on the AfLS that there's an umbrella of policy and leaders that see science as Africa's ultimate game-changing tools for its development, outside of which it would not. So when we discuss and put it in this context, then we know that however we go far or we don't go too far, we are not out of sync with our leaders. Politics has its ways. Now, I tried to mention earlier about how the structure of financing of African governments is a big challenge for all of science on the continent. Not only science, higher education, many other priorities, to the point where it seems as though Africa is only a talk shop. African Union is only a talk shop. Many of us African institutions, implementation is a challenge, but it stems primarily from the structure of our economies and the finances that funds it or comes from it. Even parliamentary allocations are difficult. One can see one leader who tries to do the unusual by deviating away at all costs, and consequences to their tenure, but it's not very common. And so, let me see here. A key feature, a key funding mechanism that we've discussed, that Africa itself funds itself under, are all these foreign policy instruments. Africa, Europe. I mean, the AU is subsidized by Europe, the AU itself, and so are many regional bodies. So are all our governments. Every project they go to Europe for a loan. You see how our heads of states go abroad for all the summits that they go, Japan, India, everyone. Because African economic structures are dependent upon this external funding. And so we are the African light source. We have to consider how to align ourselves in this space. Otherwise, the kind of funding that will come to us will be minimal, to zero. Because the African government themselves, parliaments, budgetary allocations by ministries, do not allocate for these kind of things that we are aspiring to, among many others. You can think wherever the African Union is almost fully subsidized by the by Europe. And so we have to find a way, even though we want to do all this good work, the funding that is needed lies at this interface of African and external fund allocations for development. Now, it means dependency on the outside. Many of us are critics of dependency, but the reality is what it is. Outside of that structure, then we'll do plenty of work and leave it for the next generation to continue, because the resources to do some of it, to manifest itself, might not be there. So let me leave it at that.
Okay, thanks.
Can I say something?
Go ahead.
Sure.
Thank you very much. Professor Ninken, this is your name?
Yeah, Kumba.
Kumba is like a Senegalese name.
Nangaref.
Mangfirek. So congratulations for your brilliant talk. All the things you say, it is the reality in Africa. I just want to give the example of Nepal, which have been created by South Africa, Senegal, Algeria, Egypt, and I don't know, another place. The Nepal, you know what President Abdoulaye Wade say about the Nepal? He says that Nepal is like a beautiful Mercedes with a very bad driver. But when saying that, he has forgotten that it is all these presidents, Thabo Mbeki, Abdoulaye Wade, Nigerian president, Algerian president, Egyptian president, they went to the G5 meeting in Roma, begging for money for Nepal, begging money for Nepal. How you can develop if you are, as you say, if you are begging money from other place? The African Union is founded by European Union. So what kind of science policies they can have without the authorization of European Union? What kind of science policies they can have without the authorization of World Bank, without the authorization of all these countries which are giving them money? This is the main problem. This is why talking about implementation, it will not be possible if Africa is in such kind of action. As Krumah say, Africa must unite. And this means that we have to put our own resources together and to develop. But if you want to depend from Europe, from Japan, from India, from China, from US, and last time from Saudi Arabia, how you can go ahead? You cannot. It's not possible. And the Zeleka, it is in French, of a continental economic, free economic in Africa. This is a completely false program, because it is absolutely only in the interest of European and other countries which are bringing with the goods in Africa, and this goods will circulate freely. And at the same time, the African population cannot circulate freely. Last time I was supposed to go to Cameroon for the meeting of the Cameroonian Academy of Science. But I lost a lot of time and a lot of money to get a visa to go to Cameroon. The same to go to South Africa. I was there last week to get visa to go to South Africa. Impossible. Here in Senegal, you have to waste so many time for that. So this is just to tell you that all these programs that are making this summit in Senegal in 2015 for higher education. What is the impact? No impact, nothing, because they are waiting money from other side to put in place a program. So this is just to say that it is we are really in a very difficult situation, and you show that in maybe in 2040 there will be how many 22 million people for higher education in Africa. How we are going to do if we continue such kind of policy? It will be a catastrophic situation for Africa. This is what I want to say. Thank you.
Okay. Why don't we move into the next few talks if there's no other questions? I think we're getting to the time. We're kind of behind time.
Oh, I went too long. I'm sorry. Okay. Well, thanks, Mr. Wadu. Thank you. Mr. Wage, I'm sorry. Yes. So my final remark would be that we don't get discouraged. The previous speaker before me, Mr. Wage, mentioned learning from what Europe did, South America, how they went around their own with our sesame. Africa is viewed and treated differently in the global space than all other regions. Our access to global power is different. Our receptivity to the deciders of these things, be it UNESCO, be it whoever the power structure is quite different. So we might learn from them, but we should understand that on much of this, we are on our own and we have to be creative. We can be inspired, but we have to be very creative on our own. Their model may not work directly for us because, again, on the global scale, on geopolitics, Africa's underdevelopment is not a failure of policy, it's purposeful policy. It's not a failure of policy. It's not because we don't know what to do. It is purposeful policy. So for those of us on the ground as Africans who want to advance Africa through science practice, science, which is even the tool that is the most potent tool, we have to be aware of the task ahead of us and not give up and not be frustrated and not blame others and not blame the African Academy of Science and not blame the AfLS and not blame the other academies and not blame the NEPAD and not blame here, blame there. This space is difficult for all of us combined as Africans. And we are just struggling to make ends meet. And we need to find a way to collaborate and function as a team. The spirit of Pan-Africanism has to come to us within the scientific community. The various associations that exist will find a way to collaborate and work as a team. I think that's the only way we can go forward. Otherwise, we're all in the same difficult zone, trying to do things in our own spaces in the same direction. We'll be picked apart. That's my final comment.
Yes, I agree. This is why we are working with African Light Source, African Physical Society, trying in any way, in any condition to bring people together, working together. All right.
All right.
Okay.
All right, thank you.
Stop
sharing now.
Yeah, the next speaker, I think, is supposed to be...
It's Dioma.
Dioma, yes, thank you.
Yeah, thank you. Let me share my screen, if I can. Okay. Do you see my screen?
Yes.
Yes.
Okay, good. Thank you, everyone, for this meeting. And I will try. My name is Juma Kobor, and I am the chair of the African Regional Infrastructures Strategic Task Force. And this group will have some objectives to develop develop compact light sources or regional infrastructure to get African light source. The objectives are developing the understanding of the relevant issues, science cases in Africa and worldwide. For example, to see what is doing in other countries, in other regions in the world, and also the existing facilities in Africa, survey of locations, and skills development like existing competencies, researchers, people working on light sources, applications, and so. And also some analysis of deliverables like what is the advantages of light sources, of compact light sources, and what are the disadvantages, and also what could be the cost and the benefit of such facilities in Africa in short and long term. In my presentation, I will present what is how to answer the question as is did CLS compact light source in or out of the African light source roadmap? It is clear that the answer is yes, but the question is how and where without compromising, for example, our final objective, which is African light source. Sorry. The motivation, I will talk about motivation of these African regional infrastructures, the scientifications, principle related and reasons to get CLS and AfLS. Existing examples, cases, studies in Africa and worldwide. I will talk about some existing facilities in worldwide and also in Africa, and what type of CLS for what applications, etc. The cost, I will give some range of the cost of such facilities. For benefits and risk and SWOT, I think this will come back for that, and some recommendation also. Concerning the CLS for AfLS roadmap, we know that despite the excellent performance of CLS, the final destination for Africa remains absolutely very competitive top of the range ADLS. Africa must have a premier instrument. The scale of an AfLS means a larger critical mass of experts on site, locally working together. And this advanced cohort consists of scientists, engineers, technologists, and this means the AfLS provides more training, more research, more development, and more innovation than a CLS. The CLS is an important milestone on the roadmap. However, it's not the end point. That is what we think. And the AfLS is what ultimately brings the co-located megatropolis of new industrial startups as a new innovative industry hub. This is what will have the highest likelihood of African Nobel Prizes. And this is a hub that builds the other nodes of African excellence everywhere. The motivation of this is and the background of facilities. The typical facilities would be tube and rotating anode scales, for example, for spectrometry, imaging, and diffraction, simple preparation system associated with analytical measurement. However, there is an intermediate class of instrument known as the compact light source, CLS. And these are also included in the roadmap towards the AfLS. And I will give some example on that. Why the reason is when you see that the storage link and light source facilities can be size of many football fields, and the costs are around $1 billion USD in construction, and around 10% operate per year. CLS can cost only 20 or 30 million USD, and 10% of that to operate per year. So CLS machine fit logarithmically between the small laboratory-based facility and the advanced light sources in terms of the brilliance of the X-ray. CLS would be an enhanced opportunity for engineering and technician training and technology transfer toward the advanced light source, for example, the AfLS. This is the importance of CLS. It will help people, it will help us to train the human resources for the AfLS. And it would boost also regional African research and African participation in advanced light sources. An example of motivation, it is, for example, the use of light sources in Sarkov, for example, in 2019, and how, for example, to use it for analysis of snake bite, envenomation, HIV, tuberculosis, malaria, different diseases that could be with AfLS, we can easily help people working on medical science. Concerning the existing example, I want to present you. The first one is a compact light source, the inverse quantum scattering in star in Calabria. This star is in Southern Europe, Thomson source for applied research, and it is a quantum source of monochromatic rays. In the ICS source is accelerate some section, accelerating section, high energy branch, low energy branch, beam dumps, and impact chambers. And the star beam lines, you can find the microtomography, for example, in Electra in Trieste, and also for low energy in LINAC low energy, we can use for soft X-rays like metrology. The other example I want to show is the Lynchian compact light source. And for this light source, it is the next generation and opens up new application like high brightness, monochromatic, tunable high energy, provides capabilities that can only be found at a handful of synchrotron beam lines. The high flux density at high energy is ideal for micro CT of material science samples, supports the growing demands for high energy and high resolution diffraction. The third example is the example is that we have with analytical furniture, yeah, on X-rays application, for example, the X-ray diffraction and the small angle X-ray scattering. We can have many possibilities with this facility. It is, for example, using single crystal X-ray techniques to it could be used to solve a structure of unknown compound. If we use a powder X-ray diffraction, we can also, it can permit to make residual stresses and also the orientation of textures materials. And we can use a high resolution X-ray diffraction also to determine parameters such as layer thickness, composition, strength, relaxation, and structural quality. Other applications are possible also, SACS, X-ray reflectivity, total scattering, and also X-ray spectroscopy techniques. In this, you can use many materials like lubricant oils, mining, foods, polymers, oil and fuels, building materials, and so on. And also we can use tomography by computing, using computing. The fourth one is a smart light in Netherlands, smart light. It is a collision between ladder and electrons. And the smart light use new accelerator technology to convert ladder light into intense and current X-rays by making them collide via inverse quantum scattering. And this is very interesting because the research project aims to develop a compact and bright X-ray source with tunable X-ray energy. And to achieve this, they have a consortium of 13 partners in Netherlands. I think it is possible also to do such in Africa, for example, in Eastern Africa, Southern, Eastern, Central, etc. The fifth one is the XFL, compact X-ray in USA, to visualize drugs binding to receptors at the surface of a cancer, for example. Cell will fuel development of novel drugs with more specific binding and fewer side effects. It can help visualizing also biopsy samples with fine resolution of the cell structure at much higher detail than even a compact technique scan. To unravel mechanism of superconductance of quantum materials also. So we can use it in material science, also in medical science. The sixth one is the TOM-X in France. What are the TOM-X is an electron accelerator aimed at generating X-rays. It is installed in IGLEX on Paris-Saclay faculty in Orsay, France. TOM-X is demonstrator of a compact source of high flux of X-rays generated by inverse quantum effect. And it is a prototype whose aim is to demonstrate the feasibility of such a machine. And you can find here some applications like X-rays for human body and also for material science in painting, Van Gogh painting, for example. The last one is ITEMPA Labs. The research excellence and infrastructure at ITEMPA is very, very interesting because many activities are spread over 3 accelerators laboratories and facilitated by stable beams from 200 megawave electron volt separated by sector cyclotron. You can have such techniques and such activities like technology innovation platform, the gateway to international research infrastructure, international collaboration, ALICE development and testing faculty, conferences, and fundamental studies using, for example, sector cyclotron. Plus, over such facilities worldwide, we can cite also some current example in Africa, like Open Labs, started in several years ago in Africa with IUCR, and Xtech Lab in Benin, and the crystallography summer school in Senegal. And also presently in Senegal, you have a National Center of Electronic Microscope with 1 tera data center for data storage in Senegal. So all such example can help, for example, training the future AfLS human resources. Now, how human resources we can develop that and skills. The number of people required depends on the hours of operations, and users can be trained as operators, or you can designate specific people to operate the CLS. An accelerator physicist or laser expert is not needed, but some knowledge in these areas need to be acquired. And the skills required can be found in a synchrotron beamline scientist or other instrumentation engineer. It is meaning that with CLS, we need only little people. But with AfLS, we need more large people to manage such a facility. For the cost, we can see in our investigation, we found that a CLS cost is between 12 million of euro to something like 20 million of euro. It depends what is the application and the type of equipment, like lasers, the Linux, something like this. If you want to join the AfLS project community, please, it is easy. You can register for our activities like the AfLS community survey that Kamel sent, Gian sent to the Zoom link in message. And also you can participate in the AfLS conferences. I think this is only some work we are doing. I don't present all the work that we done. We have a report, and this report will be presented in the AfLS in December. All the concerning all the aspects of the African regional infrastructure development for AfLS endpoint. Thank you for your attention. Hello.
Yeah. I don't know. Is Simon still here?
Yeah, I'm here.
Okay.
I think it was a wonderful presentation, but maybe we take all the 3 STFs before we move to the discussion.
Okay.
Okay.
Thank you,
I'm ready
Juma.
to.
It was awesome.
Yeah.
So I'm the next one, I guess?
No, I think I am the
Or
next.
am I the last one?
I think now is me.
Okay,
Sunny.
go ahead. Yeah.
Okay. One minute to share. Okay. Yes, I have 2 screens. In the Zoom it's okay, but
You have to go to presentation mode for your talk.
Yeah, you go and then say there should be somewhere, but I don't understand the language, to swap screens.
no,
Somewhere it should say.
I did that. It's okay in the Zoom, I think.
No.
No, we see the presenter mode. So you must swap with the other screen. Is one option should be to swap screens. In English, normally it will say somewhere to
It's
swap
usually
screens.
it's at the top left, I think is there.
No,
now go to the way down to the bottom
mode.
and go way down to the bottom, and you see that thing that looks like a screen.
Mm-hmm.
Way down at the bottom. Right there.
But now here on this screen, you should be able to swap screens, or on your other one, it should give you the chance to switch the presenter mode onto the other screen.
Yeah, I used to do that, but
Otherwise, the simplest thing is unplug the second screen, and then it won't get in a mix-up.
Yeah, maybe.
But don't you, Simon, Lawrence, don't you have her presentation?
No.
No? Okay.
Okay, let me do this no other way. Get this one.
Yeah, that's good.
Okay.
That's good. I think don't change it. It's good.
Good.
Yeah, we see the presentation screen. It's good.
Okay, I'll try to speak without my notes. It's okay. First of all, good morning, maybe good morning for Sikas, good afternoon for everyone. It was a pleasure to be here, so thank you for this opportunity. My name is Sonia Simeda, I'm from Cabo Verde. I am also the president of the Union of Physicists from Portuguese-speaking countries, and I'm also a member from the Collective African Membership Strategic Task Force. This is the team. The main objective from this task force is to survey existing light sources that have openings for the inclusion of African nations or consortia in their executive boards. Because if we are aspire to have a large infrastructure like light source in Africa, we need to do some capacity build of some entities and governments for this new challenge. So we think if we have some facilities that open to African nations could help to on the sharing of knowledge. And we am also to present the eligibility criterion and the membership rules and to identify potential Africa countries interested in this membership. This is ongoing task. So far, we identified the 30 light sources, 20 synchrotron and 27 synchrotron and 7 free electron lasers. We write a draft letter to explore the possibility of construction of an African beamline or welcoming African countries into their executive boards. We're waiting for some response. And we also do some brainstorm to try to identify potential funds to support an African collective membership. Okay. From the research that we did, we surf on several websites, and what we notice is most of the synchrotron, the facilities, they are national. Only 2 of them are international or stated as international. You have the European synchrotron, where the South Africa is a scientific associated. European synchrotron is based in France, Europe, and we have the CESAM, where we have the Egypt as a member for the board executive. One of the goals from this task force is to try to come up with the bias report, where we'll survey all this possibility and then give this information to Simon, the other executive board, to try to decide what is the best approach to follow. For now, what you can say that both facility, they are close to Africa. One is from the third generation and the other is for the fourth generation. So I think we have a lot of opportunity, and this facility already know how to involve African country on this executive board. Maybe could be an opportunity, but maybe not, because we don't know if they want to have more African countries there. So we need to clarify this with them. We have experienced some challenge during the survey because we have a lot of facilities, but insufficient teams member to cover all them. Another difficulty is about the lack of information or not up-to-date contents on the website. So sometimes we need to do double check and do other correlations between several sources to find the right information. And I think the most challenge that we have to solve, issues that we have to solve is how to predict the level of the engagement from African countries in assessing collective membership, because we know that Africa is rich in diversity and in policy. So we need to understand what is the policy for science for all Africa. So regarding to this challenge, on next steps, I think we must consult Africa's ministry about their position on the collective membership, and also what was the strategy for Africa. For instance, in Kim start to say what is the strategy for the next 10 years, for the next decade. Maybe we need to align with this to try to find more countries involved, and also to try to find funds to support this initiative. We need also to fill the gaps in the survey, because now I identified these two facilities, but maybe we should wait also for the answer from the letters that were sent to the director, and then we'll write the report. Okay, this was an overview of what I'm doing on this task force, and thank you for your attention. Back to you, Lawrence.
I have a question.
Yes, yeah. Please.
Can I?
Yes.
What do you mean by collective membership? To what?
Okay, because the idea is to have several countries that want to how do you say, go together to build a consortium and try to find a facility that want to accept an African membership on this executive board, because the idea is to do the manage capacity building for the entities and the government. I don't know if it's clear.
Yes, and also I have a question. What is ADLS?
Advanced light source.
Eh? Advanced light source.
Let me say a couple of things then. Yeah, advanced light source, which encompasses synchrotrons and free electron lasers, AfPS. So that term. But let me make the about the collective membership. You know, the multinational light sources like the ESRF and Sesame, they're run by member states, and the member states have certain amounts of money that they have committed to the operation of the facilities. And sometimes they allow countries to become members or associate members. And in particular, South Africa is an associate member of the ESRF. And what that meant, I think South Africa, by being an associate member, committed to something like, I don't know, 0.3% of the annual budget or something. I don't remember. It's not a huge amount. How much is it?
0.3.
0.3%. Okay. So the idea is for, instead of one country, because that may be daunting for some of the smaller countries, instead of one country becoming a member, several countries could pool their resources and have a group membership. So that's the whole idea of what Sonia is talking about.
Thank you. Now I understand. Even I was thinking about such kind of possibility for Africa to be member of the ITER, the International Thermonuclear International Reactor.
I mean, it's the same thing. I mean, we need to get countries together to become members. Because that way you are in on a lot of the internal deliberations.
Okay, thank you.
Lawrence, are you there?
Yep, I'm here. Okay. Any more questions? So I'll go into my talk on the last strategic task force. Let me share screen. And I don't know, let's see, which one am I sharing? I start. And that is and then I'm good, right?
Yes.
Okay. So I'm presenting the third task force that we established. And that was the idea similar to collective membership in a light source, except we're in this task force, we're just looking at a single beamline. So let me just say at the outset what the purposes are. You know, why an African beamline, and what is meant by the term African beamline is the beamline where African nations or African institutions have a ownership interest in the beamline. And so with the ownership interest comes participation in the management and the priority setting of the beamline. So the purpose is to solve science and technology problems. But it's also because you would have multiple, well, one idea is that you would have multiple partners, including the light source facilities manager. We would be flexing some science diplomacy muscles. But the main thing I think with that I focus on is it builds capacity in science facility governance. That is knowing what it takes to run a major science facility, from the mundane issues of whose parking space is where to just making sure that there's adequate power supply and other public works and, you know, just basic supplies and everything in between. So we all know what a beamline is, but the idea is that we're talking about this part here. You know, we call it the business end of the light source, unless you're in this business over here. But I think, you know, the cutoff is probably where the straight section goes, and then if you own the beamline, I think you're in charge of the optics hutch, the experimental hutch, and all the workstations. So I think these are like service providers. These are users. Okay, so now, how do we determine what kind of beamline the African light source should, or that Africa should buy. And I sort of think of it in two ways, maybe two different ways. I mean, there's the 6 canonical ways that photons interrogate materials. So this is like a normal exam question to name these things: transmission, reflection, refraction, diffraction, absorption, or scattering. So one of these techniques, or some combination of these techniques, would be a good place to start. Okay, how do you want to interrogate the materials? And then that sort of funnels into different techniques: X-ray diffraction, powder X-ray diffraction, Sachs wax, different types of spectroscopies like AfPS, dynamic light scattering, and then you can add multiple photon interrogations and also time resolved interrogations. So when we talk about an African beamline, I mean, one of the things that people like to say that so that could address Africa's needs. I always kind of bristle at such a term because, you know, Africa needs, everyone needs, the world needs a lot. And who gets to set what the needs are? Who gets to say what the needs are? And how are the scientific priorities to address those needs? The way that's done is through government. So it is important to understand what is the political economy of Africa in terms of how decisions get made by politicians that impact the way the economy works. First thing that's important is that Africa, when people say Africa's needs, Africa is actually 54 sovereign states. So Ghana may think that the needs are different than South Africa might. And they may or may not agree. But that is the process of diplomacy. Maybe they can figure out a way to agree or figure out a way to at least work together. But then there's under government. So this is a picture of a parliament, but under government is non-governmental organizations such as the African Light Source and the African Physical Society. And there's a NGO for a lot of different fields, like chemists, neuroscientists. And one of the things that we as an African Light Source organization, being a multidisciplinary enterprise, is we try to partner with everyone. So we have a whole list of partner organizations because everyone has a different, I mean, if you read the papers that come out of light sources, there's all kind of different users that are doing things that, just boggles the mind sometimes in terms of their applications and things that you've never even heard of. So let's see. So let me just cut to the chase here. And in terms of an African beamline at a existing synchrotron facility, this task force has really focused on Sesame. Right? Now why? Because, well, Sesame already has an African member. So, and you could say in some sense, Sesame is an African light source. And Sesame has a good list of observers. Not every light source in the world has a membership structure, right? The United States, like the US light sources, definitely do not. And others are just national facilities that may have international input. Well, they all have international input, but there's no membership structure. So you can't, I don't think you can like join NSLS2 or the Advanced Photon Source or the Advanced Light Source, the one out in Berkeley. I think to even introduce that type of structure would take an act of Congress, which probably wouldn't go along with that idea. So now, if we talk about we focus on an African beamline at Sesame. It is important to understand that it is very common in the light source world, with there are 50 light source facilities, for one country to build a beamline in another country's light source facility. We can get into what reasons why people do that. A lot of it is for capability reasons, load shedding. A lot of times it's just cheaper. A lot of times you just need personnel that isn't available in your country, but it is available in another country. That's an entirely different conversation, but it's a very common thing. It's a very, very common thing. Now I can just pull these off the web. This is the layout of the experimental hall of Sesame. This is the front door. Is that right, Andrea?
So let me unmute. Yes, that
So I think if you
is the
walk
front
into
door.
this,
That is that one. Yes.
yeah, if you walk into this door,
Yeah, you enter that
hall.
round hall, and then you go to the main hall.
Okay, so now the important thing about these two pictures is the one on the left, I think, shows 1, 2, 3, 4, 7. Well, the ones in red are, well, let me see. The ones in red are as of whenever this figure was made, were operating. Is that right?
We have 5 beamlines operating in this moment. What is missing here is the tomography beamline.
Right.
And this must be a pretty old picture, but so we did not put them exactly in this position, but it's all right. I mean, doesn't change much at which exit they are, and so there are presently 5 beamlines covering from infrared to soft X-rays to hard X-rays, so any kind of spectrum, and they go from infrared microspectroscopy to EXAFT to powder diffraction, tomography, and soft X-rays absorption.
Right.
Yeah, for those of you who don't know, the gentleman speaking, Andrea Lauza, is the scientific director at Sesame, and he's been a big backer of the African Light Source.
Right.
Hello.
So,
hello, everybody.
The main point I wanted to make from showing these two slides is that this shows 13 insertion devices. So 13 what's called straight sections. But the point is that I guess Sesame can accommodate 13 beamlines. Is that still correct?
No, even more, because we can use also bending magnets, and we are using bending magnets as sources. So the infrared beamline and the X-ray beamline are going to have a bending magnet as a source.
Yeah.
So there can be as high as 20, maybe. That will depends very much on if we can remove those laboratories in order to make space for longer beamlines around. So there are plans in which we can make up to 20.
And so the main point is that there's room at Sesame for new ideas, all kinds of ideas. It's a great place to try interesting things, I think. So now, why are we focused on Sesame? Because as we said, Sesame is a close AfLS partner. Egypt is already not a Sesame partner, but a Sesame member. I guess Egypt is a member state of the African Union and also a member of Sesame. Sesame has its own user community and science committee, has a users meeting, which is like in July, I think. And Sesame has a strategic plan that, as Andrea just said, includes, well, he can talk about what a strategic plan is, but I think includes new diffraction and spectroscopy beamlines. And then it just commissioned 2 new beamlines. Was that last year or a year before?
HESEP was inaugurated in 2022, and BEATS was inaugurated just in June 2023.
Right, okay.
So they are very new, and they are now open to users.
Right. So now, how to get involved in Sesame. So we've already heard one talk from Sesame earlier today, and there'll be I guess Andrea will be giving a talk on Thursday. I like to keep up with what's going on at Sesame. You can just do it at their website. So if you go to the homepage and there's a tab that says Beamlines, and then they list their publications as they come out. So I think, what is always possible is to sort of look and see what kind of science is going on in Sesame and think about how you can involve yourselves there and how you might want to modify a technique to fit your scientific objectives. Now, that's a very interesting proposition because, again, how do you determine what Africa needs and how does that translate into funding to construct a beamline? Well, that's a lot of hard work. You got to write proposals. You got to go to a lot of meetings and convince a lot of people. You got to convince the science director, and then the council, and then whatever funding agency. So really, the only way to do it is just to jump in. Now, I guess I'll end by just saying that you can think in terms of a beamline that does, I guess what I'll call normal experiments, like a normal general diffraction beamline, a normal, spectroscopy beamline or whatever. But I think it is possible for Africans to think about entirely new and exotic techniques, mainly because we do not have to worry about, I guess, what's the word I'm looking for? We don't have to worry about users, right? So I think if you're the facility manager, if you're the science director, one of your concerns is who is going to use this technique, right? Whereas if you don't have to worry about that, you can think about, I want to do something exotic, and I might be the only person in the world that uses this technique, which is kind of the way science sort of advances, where you probably the sort of the difference between there's probably at some point where someone who won a Nobel Prize, his or her colleagues must have thought they were totally insane, right? So there's a possibility to sort of think about how do you combine some of these canonical methods of interrogating a sample with multiple photons and all kind of exotic optics to interrogate a sample. So I guess the point I would just say is not only could an African beamline, sort of just build existing sort of techniques, but developing entirely new techniques, for which I will argue, and Andrea can tell me if I'm wrong, there is room at Sesame to do. Whether or not there is money to do it depends on probably how well you can write your proposals and argue your case. So I'll just end there, and Andrea can sort of comment on any of that which I just said.
Okay, sure. Yeah, you're right. The challenge of making a completely new beamline is always there, and that can be extremely rewarding. From the point of view of building a community in Africa of users of synchrotron radiation, I think that practically any kind of beamline you decide can be beneficial, because you have to remember that once you have established a beamline in a facility, this will more or less work in this way. There is a certain amount of beam time which is for the owners of that beamline, and the rest is given to the general users of the facility as in order to compensate for the use of the photon emitted by the ring, in a way. So normally this share is in the order of 50-50. Yeah, so 50% of the beam time is reserved for the community which has built the beamline, and 50% is for the general users of the facility. It is a fair share. And this is more or less everywhere in every facility. But what you can also negotiate is to expand the to trade off part of the in-house of the proprietary beam time with beam time on other beam lines. And this is where the things start to be very interesting, because doesn't impose you to choose exactly which beamline will be available, because semester by semester you can trade off part of this beam time with beam time on other techniques, which means that it will not be an exclusive business of the community that has built that beamline, but it will be really a democratic access to the entire facility. And this is exactly what could happen in, for example, in Sesame, if there is an African beamline. Yeah, it's a way of it's an inclusive enterprise of beam time.
Yeah.
And then which beamline you are going actually to build, that is a negotiation also with the facility, because it is not so it's not in our interest to build a second beamline of the same kind that we already have, but to increase the suite of beamlines, that is for sure. So in any void can be proposed, so to fill any void.
Yeah.
The most simple would be to go for some kind of scattering or diffraction, and that is because crystallography is, after all, is the synchronous radiation best friends. There are the clustering communities, and there is already in Africa a crystallographic association which can foster the use of the beamline. This is one thing, but also SAP can be a very good idea, or, as you say, something completely exotic and new and revolutionary, which it's also very attractive. Yeah, to have something that then we would attract at the same beamline users from everywhere in the world.
Right. So yeah, this paper just came out this morning. I don't know, recently.
Yeah.
Anyway, I know these guys have been. Yeah, they've been hammering at this thing for years, right?
Yeah, they are working on Fermi, the free electron laser of Bellectra.
Right, and it involves Paul Scherrer Institute, PSI. It's also sort of interesting that well, what they are doing was theoretically predicted, like 20 plus years ago. So, like I said, I think for a young person in the field, you can start thinking of something that, someone my age might be well expired by the time that it comes to fruition. But, we have that option, I think. to think in those terms. Jihan.
Yes, hi. So thank you, Lawrence, for this overview, also to Andrea. I just want to couple with what Andrea said about negotiating the best void to fill at existing facility. Of course, this is a strategic point that comes to the management, but also the other side that we're trying to do is to collect some demands from the community, like collecting letters of interest, letters of intent. And this is something that also happened with Sesame, for example, for the IR beamline when it was chosen as a phase 1 beamline. Because for us, we are having what we call phase 1 and phase 2 beamlines. So this comes through distributing or information through, for example, Sesame Council, other committees to the members of Sesame, and each in turn distributes this, and eventually they collected what's called letters of interest, and the infrared spectroscopy beamline was one of the most demanded techniques at that time. So this is why it was decided to go on with it. And also, as I said in my presentation this afternoon, it was the first fully designed beamline. So the idea that people thought that Sesame is always going to work with donated or given components, all components, was totally dropped. First by going up to a totally brand new storage ring. Also that beamline was new at that time. So what I want to say is that, of course, it's something that comes through coordination and negotiation with existing facility that will host the African beamline. But also it's important to collect more information, letters of intent, letters of interest from the users community themselves. And something that we did is that survey that I spoke about. I put the link, and I'm happy because I keep receiving emails throughout this afternoon. Some of the attendees are filling out this survey. So I encourage the others to do the same. And also we need to put some effort more into collecting letters of interest. I recall that we did a lot of effort on that. It's already there on the website. And also for the ASFAP, we also collected a lot of letters of interest for establishing an African license. Thank you.
Mm-hmm.
Can I say something?
Go ahead.
You know, I remember in the past, it was possible to negotiate with the Office of External Activity at ICTP3S a beamline for African scholars in the so-called sandwich program. And I remember two scientists from Senegal, they got beamline at Electra. So I am wondering, maybe it is possible to negotiate with Sesame, with Brookhaven, and with other synchrotron facility to have beamline for African scholar. Maybe African Light Source can negotiate such kind of collaboration to have beamline.
I'm sorry, Philip. Do you mean beam time or beamline?
Yeah,
yeah.
You mean beam
do you
time?
mean beamline or beam time?
Yeah.
Beamline. Beam time. Let's say beam time.
Yeah. I think you think it's beam time.
Beam time.
Yeah, this is easy and can be done.
This is possible to do.
Yeah, but
and so that this will help for the capacity building.
Yes, well, but it's also not enough. Yeah.
I mean, all synchrotrons are open to beam time for good proposals. That is not really the problem. There is a strong difference between getting beam time as users with respect to building a beamline, because in building the beamline there is also the process of constructing. So there is also the technical part which is somehow entered into play. So you But at the same time, you foster the technical community and the scientific one. So it's a very different situation. So to design the beamline, to build the beamline, to install the beamline, these are all steps which would be accessible when building a beamline in a facility.
No, I understand.
And then you start using.
I understand now. This means that we need a strong capacity building for that.
Yeah. I mean, this is it. In a way, it comes automatically by doing. It's and then after you also have the management of the beamline. So the community which builds a beamline is expected to provide the beamline scientists, and so which are those scientists which are residents at the facility and help the users using the beamline. They are those which know the best how to obtain good data from one particular instrument, and they share this knowledge with the users which come and use the facility. So there is a lot of, so in a way, you have to think of something in which there is the cost of the beamline. So a few millions of some kind will depend very much on which kind of beamline is to be built, and a cost of personnel to be there. And at this point, I would strongly suggest also of thinking of the cost of the transnational access, so which is not enormous, but has to be counted from the beginning. So the $50,000 per year in order to cover for the travels of the users. And you put all these things together, and it could be a very successful enterprise.
Oh man, sir. Hi. They don't say
Synchrotron facilities.
I don't get that.
Of having a beamline.
No, I never have ordered in there from there, but I'm surprised they don't have.
I just want to let you know, Lawrence, Anna Lena has a question, and she should be invited to put it.
Right. Do we have time? Or does she have put in the chat?
Yeah, I think we should close soon, but let's give her question. She asked it a while back.
Yeah, go ahead.
Yeah, Vitaly's not going to.
Hi, sorry. Yeah, I was wondering, at the beginning of your presentation, you mentioned that a African beamline at an existing international light source might help Africa flex its science diplomacy muscles. And I was wondering, what exactly do you mean by that? So how would the beamline help Africa to flex its science diplomacy muscles? And then also, what do you mean by science diplomacy in this context? Thank you.
Right. So I think I was answering that question in the chat. So to actually build a beamline at an existing facility requires a lot of negotiation, like Andrea was saying, and there are probably some days when it's actually quite interesting. So, and also in international project finance, which is an area of law, even simple questions of currency and payments. So when you're participating in a big multinational program, whose currency do you use? What mechanisms do you use to get money from point A to point B? All kind of just sort of legal and interesting. So what does it mean for like some African country to own a piece of property, let's say in Jordan? So, there's lawyers who that's all they do. They work on stuff like that.
May I do one quick question?
Go ahead, and Simon, you can moderate if this is the last question.
Okay, because what I want to know is if we build a beamline, do we get a place on the executive board?
No.
No?
Not in Sesame. There are two completely different things, and are both absolutely possible routes for any facility. So one thing is it is the difference between intergovernmental and international in a way. So international means that a series of a set of institutes or one institute joined with an instrument, an intergovernmental facility like ESRF or PESAMI. The other is a government enters the facility and decides to fund the facility without a particular aim, and anybody can then apply for any beam time in that facility. So there are two completely different business models, if you want. Being a member of a facility is one thing, while constructing and they can be both applied at the same time. For example, in this moment, Turkey is building a beamline in Sesame. So this is a member which is building their own instrument. So they will have privileged access to that particular instrument, and this will also benefit the facility because the facility will have 50% of the beam time there to be used by the general members, by the general users. So there are two different things. Both routes can be. One is a running cost which is higher, but the initial investment is less. But you don't have all the technical part in that case. You will have a few people. The advantages of being a member is that you have a full possibility to get beam time, but it is a more limited possibility for training. While in the other case, the entire staff involved will be obviously trained at the facility. So I would propose to do both, obviously, if it's possible. Yeah, it's both have a good result in that, but the intergovernmental way is more complicated for the bureaucratic point of view. And then you have to convince a government to enter the facility, while building a beamline can stay at the level of at our level, so a level of physicists. You just find the money and build a beamline. So it's something that you can do at the scientist level, which is more easy for me to understand.
Right.
I'm not a government person.
Yeah, I always think in terms of like, there's some meetings. How much do I have to pay to not have to go to that meeting? That's when. So when you're beamlines, there's probably just some general management meetings that you can just skip altogether. So, Simon, I guess you want to close out the session? I don't know if there's any more questions.
Yeah, thank you. So I wanted to comment that the strategic task forces have been in operation several months and they've done excellent work. And now we have seen the results of what they have done after those few months, and they've made a lot of progress in defining their objectives They're going to produce a report for a month. This was our opportunity to let the community know and put the matter to the wider community. So you are welcome to get in touch with the conveners of the strategic task force that you have heard here today and make some inputs. And it was great, I think, to learn all the inputs that have been made and see where we're going. And the idea is, once we have the reports of the strategic task forces, that's where the science diplomacy really begins, the interacting with governments really begins. We want to use those reports then to approach governments and African regional groupings, African continent-wide groupings, professional bodies, voluntary associations, and so on. And we want to really try and put these reports on the table and get them funded. You have seen we want to have them realized by 2026. So we've got a lot of work ahead. I want to really thank all the people on the strategic task force for all their very, very hard work. I hope we see that. I really look forward that we will recognize today it was a very, very important milestone, even to have your presence here, Andrea, to present that one that we've just heard about, Sesame. I really hope it's a wonderful milestone for us, you know, that the things that we're thinking of with these strategic task forces, which is very, very ambitious. It goes way beyond just training and building a user base and so on. This is actually going to be concrete things that Africa will have. So thank you very much for everyone who participated.
I have a big problem. I was in a conference, the African conference, in Zoom. And at a certain moment, I stopped having the voice. I don't hear anything. People are speaking. So for them, it's normal. What can be the reason? That I don't listen anything.
Oh, I think that's
At
Leo.
a certain moment, I stopped listening.
Yeah,
Leo, we can hear you.
Yeah, well,
tell him the meeting is over.
I was in the conference today, and
yeah.
Okay, I just muted him for now. I think I was basically coming to an end, but that's my input, Lawrence. Thank you for your session.
Okay. All righty. I will see everyone tomorrow.
Okay, bye. See you.
Bye-bye.
Bye-bye.
Thank you, everyone. See you tomorrow. Bye-bye.
Bye. Bye-bye.
Bye-bye. See you.
Bye.
Bye-bye.
Okay, bye. Bye to everyone.
what happened to Zoom? Yes, yes.